some fundamental unit, the most fundamental useful unit, then you could derive the equation from the relationship of many of those fundamental units. Is that something that you're working on?
Absolutely. Absolutely.
And so do you have a sense for what that unit is for you?
Well, I mean, so I wasn't trying to generate the unit. My goal was to back into it, right? But what I've backed into so far, and I'm pretty sure this part's right, what details are exactly wrong from here on out, is that the fundamental unit looks like this.
Is that that's crazy. We were at Brian Keating's house, and Brian Keating had that thing on his table. What is it? We are at UCSD. We are at Dr. Brian Keating's office, and I think that we're going to talk about the history and the context of science, the ideas that underpin the way that we come to conclusions about the world. And it seems like it might make sense to start with something that we've probably heard a lot about over the course of the last few years, which is this idea that we should believe in science. What is that?
This is a hyperbolic figure eight knot.
We're actually at his office, not his house.
Sorry, I imagine that he only exists inside of his office.
We're not quite back at our friends yet.
All right, so let's back up a little bit. In geometry, there's this concept of manifold, right? It's a thing that can have boundaries without edges. Let's say, like a torus. We can take make a flat sheet of paper and wrap it together and tape one of its edges together, get rid of its edges. And then if it was stretchy, you could take the two circles and tape them together. And now it's a shape that has boundaries, right? It has a surface boundary, but it doesn't have edges.
Hi, my name is Henry Sagerman. This is Figure Eight Knot Complement. Again, this is joint work with Saul Schleimer and Francois Goethe. So often in knot theory, it's a good idea to look not only at the knot, but also the complement of the knot. So the complement of the knot is what you get when you subtract the knot from three-dimensional space. And you're left with a three-dimensional manifold that has a torus boundary.
Okay. Well, the simplest possible three-dimensional or three-manifold that you can have is called the Giesecke manifold. And imagine you formed a Giesecke manifold with some random wave interactions that just came together just right to form it. It's not until you double-walled it, double-covered it, that it would become stabilized and wouldn't just dissipate immediately after forming it. Okay, so in order to stabilize it, you'd have to double up on it. And when we double cover the Giesecke manifold, we get exactly the hyperbolic figure eight knot. So I think the internal structure of hyperbolic space is the smallest possible knot you can make in hyperbolic geometry.
So you can think of this as I got this sort of ball, and then I've drilled out the knot inside of this, so you can think of a worm eating its way through this object and leaving behind the trail, which is the knot. So one of the most interesting things about the figure eight knot complement is that its complement is actually a hyperbolic manifold. And it's one of the simplest examples of hyperbolic manifolds.
And the external expression, that knot being formed means from the outside, there's a cutoff region where nothing from the outside ever gets to go inside it. So the domain gets divided internally and externally. And the external expression of this internal cutoff in the hyperbolic figure eight knot is what I think is the n hypersphere of maximal volume.
So where did this come from? So this is closely related to the symmetric figure eight knot. So the symmetric figure eight knot, as I said in that video, it was designed inside of S3, the unit sphere in four-dimensional space. And then we chose a projection point in projecting it via stereographic projection to three-dimensional space so we can print it.
Interestingly, these things are opposites in volume. So the minimal possible volume complement you can have in hyperbolic space is the hyperbolic figure eight knot. And the maximal volume structure, volumetric structure you can have is the n hypersphere of maximal volume.
Oh, ain't that just lovely?
Hey, are we still on?
We are. Hey, anytime I can play some Steppenwolf, I think that's a good day. But
Oh yeah, no,
hey,
that's a great song.
hey guys, what's going on? Memes here. Oh my god, and there's the balloon. I don't even know what that is. Is that people signaling? Are people hitting the buttons? Are people celebrating good times and everything? But yes, we are late. I am late on so many levels, but this is now episode, I believe, 6.
TMI.
That one of the other reasons I go through, I get the thumbnail. I'm like, all right, so where were we? I'm like, all right, it says number 3. I'm like, okay, so we're on number 4. And as I'm actually bringing it up in StreamYards, apparently we had already done episode 5. So then I had to go back at the episode 5, edit that one so it would be episode 6 because we want to be accurate in our record keeping. Apparently, that's supposed to be important for all the different stuff and things we're going to claim. But yes, I am joined by Kali for right now. We may have some other guests popping in along over the evening. But Kali, one of the other reasons we're late is we started discussing things and I didn't hit go because I was not prepared. And we had a fantastic discussion for like 10 minutes before. Yes, these things happen, but I apologize. And let's say hello to our friends in the chat. We have Rick popping in. Rick is temporarily in the pass. He apparently has hit the thing, whatever that means. Pi equals 3. That's a very bold claim. Some would assert that. But we got Upcycle in the house. Yes, we are live, as well as we got Lugnuts. Lugnuts is back, giving us the sportscasting that we totally deserve. But so Kali, we were just you were talking about a cosmologist on Mr. Freeman's podcast. Shout out to Mr. Freeman.
I think it was, yeah. But
you were talking about, like, there was an experimentalist, like I think he had worked in, what was it, like the deep field or something, and he was saying it's like, Lex was like, so about the Big Bang, and you gave an interesting response.
Yeah, so I'm connecting to something and it's like doing a bunch of authentication so I can be in the chat too. There we go. Okay, wait.
You are back in there. You were rematerializing in the realm of connections and stuff and things there.
Yeah, yeah. Okay, so I also posted some things, some links to some papers that are going to be relevant to this stuff, this discussion. Oh yeah, okay, so this it was on one of these like nerd channel interview things, and they were interviewing a guy that's one of the infrared astronomers that's working with the James Webb to do the deep field work. And they were talking, and the interviewer, whoever it was, sort of said something about, like, oh, the Big Bang expansion. And the guy was like, wait, like, back that up, because that's not a given, and he was just like,
I'm looking at the data that's used for like a lot of models and everything.
Exactly.
But
that's all he was saying. He's just like, let's not presume. We have a bunch of data. The data says that as things get further away, they seem to get red. That is what we know. That's what we know. What we also know is that when things are spinning, they tend to get a shift according to the rotational velocity, which we've worked out the math for and seems to make a lot of sense for that. Like a galaxy that's spinning, like the edge that's spinning away from us will have a red shift, and the stuff coming towards us will be blue shifted, because kind of in a way space is like scrunched up in those dimensions, right? It's like, okay, so that makes sense. And every single gravitational object blue shifts at its surface. That's just a thing that gravity does, right? Like they have to compensate for that with the satellites that do the GPS. This is the whole thing they had to compensate for, was that down by Earth, because the gravity is stronger, there's like a weird shift.
I think it's like a SAGNet correction or something like that. I hear about that.
It's minuscule. It's like a phase correction basically.
But
Like,
but if it
that's-
wasn't there, our GPS. Wait, is that why my GPS back in the day? It's like GPS was great for getting you like 99.8% of the way there, and that last 0.2%, it's like that could throw you off by enough where if you're
Oh,
downtown in the city, oh my god,
yeah,
I have to
that
take
could
so
have been,
many turns so many times and busted to get to where I'm something. It was very infuriating.
yeah. That could have been it. Like when we had very early GPS, because I remember the early GPS. It was
I
kind of like
assume that
you're
Boston is
within
not a driver
you're
friendly
within
city.
like 30 meters of the point. You know, like that sort of vagueness about your GPS. But it was like if it's better than nothing. At least I know in the right neighborhood. You know. But
Oh,
then all of a sudden they had this
yes.
GPS that was like, no, we have you pinpointed. If we need to drop a nuke on you, we know exactly where you are. You know?
You can reliably be like, I'm gonna be literally about 100 feet of where it says I am, as long as I'm not going like driving like a maniac. It's like you're probably gonna see where your turn is coming.
Now I'm sure if they wanted to, they would know like within inches where you are.
Well, it probably also depends on how much you want to pay. It's like, yeah, it's per cent. Oh, is that like a? Yeah, I don't know. Is this like the monetary uncertainty principle? It's like you can be a lot more precise where you are.
Where
I'm
did you
gonna
see where they
charge you that extra.
back engineered the routers, the Wi-Fi routers, to be able to detect bodies position? They,
I have no idea about that stuff. The whole Batman device and every. I'm not gonna lie, I love that movie. I love that movie. I Here's the thing. I'm not planning on doing any type of international form of or divest. I don't plan on being a terrorist, so it's like I don't really worry about that for the most part. I mean, I think it's cool in concept. I have no idea. But see, I always thought the thing is, it's like, oh, well, if you want the fastest internet, it's like, well, why don't we just do that whole? It's like, I have extra bandwidth open. You can use some of my bandwidth. Because everyone has some
yeah,
bandwidth. Well, if you're not using it, you can kind of share it. Then you can maximize your throughput. I mean, that sounds like it's really complicated, but I'm like, is it much more complicated than we already are doing? I don't know. I'm sorry. We're not talking about cosmology at all. We're just talking about people problems. We're supposed to be talking about people trying to figure out the universe. Why? Because solving our own problems seems too hard. So let's solve everything else first.
yeah.
That's
That's my grief with the all of this. I mean, you know,
what brought me here.
I am so
I couldn't
old
find solutions to
school.
the other things. So
I'm like an old school physicalist, you know? And you know why? It's because it doesn't like ask anybody who does all the DMT in the world. You come down from it. You don't stay there because the real world is real. It's real. And if all the people that are like in these philosophical places, I think they have it probably like, it's just like, I don't know. It's like, have you ever been in a physically deprived situation? It's like, you know, like you're in the mud and you're freaking cold. It's like, no, the physical world is so right in your face that you can't ignore it. You haven't got time or thought for, is this a simulation you live in? Because no, it's not. It's real. Or if it's a simulation, you might as well just accept it as real. Because when that tree falls on top of you and crushes you or whatever, it sure seems real. And inside our
that
skulls, it's not. And I think it's like maybe that's a really smart device that we have built into ourselves, you know, this illusion of autonomy, so that we actually can do this, like sort of like pulling ourselves out of ourselves so that we don't have to have the trauma of our actual physical self is experiencing, you know,
so I
just to be like that, while at the
oh
same
no
time simultaneously, because I'm like this, I also very much believe in the sort of like not to get too Scientology, but like a thetan. You have a soul, there's an identity, It's weirdly singular and yet can merge and connect with others. And it's all part of a whole, but there's a certain singularity about self. While at the same time being messed up into the whole. It's like a weird thing.
I believe it's unum, no, pluribus e unum. That's the one. Out of many, no, e pluribus unum. Out of many, one, or unum e pluribus, out of one, many.
No, wait, yeah.
God, I'm terrible at Latin, and I took 2 years of it, like 1.5, and then
no, well, the traditional one is e pluribus unum.
Out of many, one.
Yeah. But is it the other way around, actually? Many
I thought of that, yes.
One.
It may depend upon one's perspective. That's that's
way more
it's
Hindu
a very,
and way
yes.
more like way more Hindu and way more where my head is at personally.
I spent enough time on Wolfram Alpha where I looked at that statement and I'm like, what if I inverted that? What if I took 1 over e pluribus unum? And that got me thinking more too. And I'm like, ooh, might explain a lot. So I don't know. Going down the Wolfram hole and everything. But trying to get to a more physical plane if we could. Where did you want to go from here? I could take us in a direction, or
no, but you just tweaked me on that because I've never actually looked at that. The E and 1 over E rather, because I did this whole series, one of my videos was all about basically the holographic principle and how that applies to mathematics as well, and that this might be a completely super universal thing. The boundary, basically boundary and boundary conditions and the reflection of self and the outside. Because at 1, you have 1 over 1. That's the boundary, right? It's like where the dialectic is exactly balanced.
Well, that's the thing. A lot of times we forget about the 1. We might we might not even have any notation, but we're assuming there's something there, and we don't. Notation is important,
right? And then any number that there exists larger than 1, there's its perfect reciprocal on the other side of 1, correct? Like every number's got its reciprocal. You just put a 1 over it. 17.
For sake of conversation, yes. I don't know the answer to that, honestly, but okay.
Well, I mean, it's just like a reflection. It's like 17, 1 over 17. 17 gazillion, and then it's like 1 over whatever that was. It's just, there's always going to be
my only fear, Kali, is I have no idea if this opens up one of those what's the biggest number? Infinity plus. I have no idea if this goes infinity plus 1 argument.
No. I hate those.
Okay. That aside, no, I understand. There's always going to be an inversion.
I hate all that sort of semantic sophistry shit. Okay, let's just deal with simple things. So basically that's where you got. So just think of that as being like a mirror, right? Like everything on one side gets reflected on the other as a perfect inversion. Then you just do the same. When you do the same thing in the 2-dimensional plane, you end up getting the circle of inversion, as they call it, which I love. It's like my favorite geometric tool in the whole universe, because it means that if you have a huge plane, an infinite plane, all you need to do to be able to contain and describe that plane is to be able to draw one circle someplace and then have that plane reflected the same way exactly. Oh, wait, I could even get this. I think my phone is charged enough.
Every once in a while, I log different friends. Leave me alone. I like these little different things there. Oh, I think Kali took herself off. So, um, well, that's going on there. Upcycle saying astrophysicists often use omnibus statistical tests to analyze data from multiple telescopes. Well, here's the thing. My thing is, if we still have a lot of the raw base data, it's like, don't we have modern tools where we could take that raw base data if we do need to recompute things, assuming other maybe different models or stuff like that? Can't we just kind of like re-add all this stuff in? Like it can't be.
Sorry,
It just
I don't
seems
know
like
what
just
happened.
additional work. I was like job security. I'm just saying. Welcome back.
Yeah, I don't know what happened. Okay, so right, so you just
Okay, well,
draw
let me
a
continue.
circle
Yep.
that reflects
Mhm.
the entire surface around it.
Say
That's the
more.
circle of inversion. It's basically you just do this mapping where every single point, infinity is exactly the middle. Actually, I guess it would go like this, but whatever. Infinity is the middle, would be the middle on one of these circle of inversion things. This is slightly different. And then it's like a parabolic version of things. There's infinity, and then slightly away from infinity, and right close to the surface is right close to the surface. There's
It's
look up,
a stereographic projection.
exactly,
It's kind of
exactly.
like a picture. Like when you have the road going down, it's meeting at infinity technically.
Exactly. It's like it's like a hyperbolic mapping of the universe like that. So that's the circle of inversion, which is basically the holographic principle. That sort of the entire universe is reflected in each of the singularities, right? Like as if we imagine that was a mirror surface, then all the universe is being reflected in it as sort of like a duplicate of the universe. And this is the whole point also of like when you do with neutron decay cosmology, because it's just like, wait, let's just take Mach to the extreme. And when you go through the hole, let's just pretend it's just like a looking glass. You go through the singularity. What's on the other side of the singularity is the entire universe mirrored. It would be the antimatter universe because you get ripped apart and twisted inside out. But, the individual parts come through. And then
See,
you're at the
I
furthest
would almost say
edge.
it's. Oh, go on.
And then you're at the deep void suddenly because you're at the other end of the maxima folding over of space-time.
Okay, well, I was just gonna say, I'm like, I don't personally. I think it might even be easier. I don't actually think you necessarily need a singularity, as some people may believe, so to think. In my opinion, could be totally wrong. I look at things. I'm like, what if the singularity was just the single? If we consider it a zero-dimensional point, which is literally just a point, that's literally a dot. We consider that a thing. What if everything else basically just wrapped around that thing?
Right. Yeah, exactly. No, I think that's the thing. The surface, the event horizon is this, to me, I take a sort of like, I think what's considered a fully Lorentzian view, where there's only distance. There's none of this freaking time parameter. You don't get to play with that because time is compactified. Everything is purely a distance. And therefore, as you approach, you sort of like space time gets bent, and then you're reflected and you're shooting along the surface that you can never get past. The only way of getting past the surface is to actually like relax and be less energetic is like the way you do it, right? And that's exactly what happens.
Like a finger trap.
Yeah, exactly. You have to give into it to let it happen. The neutron decays. The neutron gives in and just gives into the exploding, really, is what the thing. And this is the whole that Dirac paper that I posted, where it's just like, oh, okay, so it's just this weird transition from no Coulomb force because you're all orbital to all Coulomb force because now you're radial. It's like you're spiky or you're a little clean ball. Like those are the essentials.
That's very interesting. That actually sounds like what some of the Quisicle folks have been saying. I think they say they have a they have a hedgehog, they have a spiky hedgehog, and then they have it's okay. That's very interesting. And this was an old paper you said? Was it like from like 1920, 1930?
34. So it's like basically just as they're formulating all this stuff, this guy publishes a paper because it's a classical interpretation in a way. It's like you're treating it like it's a wave, but that's not fluid. Like that doesn't get into weird chromodynamics or any of this stuff. Granted, there's no quark in this involved. And, I have my whole thing about quarks and how the geometry of quarks works very well if you just treat the fractional charges as axes of charge. Because then that pulls out this whole like innate Cartesian relationship that the electromagnetic forces have where each one is opposed 90 degrees to each other.
Would you be willing to go into that one more time? I'm still trying to wrap my. I just remember we've spent literally about a day. I think we spent about 6, maybe 7 or 8 hours one day on quarks. It was actually from a programming issue, like a programming side thing, trying to interpret them. So we kind of just went into it for a while. We didn't figure it out. We came up with some interesting conceptions. We kept going back and forth, but I'm always open for the simplest explanation. So Kali, take us away, please.
Oh, okay. So I have a video about this, but the way I like to do it, I can't see I can't see. Wait, can I turn my camera around?
I think there's an option on it. I think. I'm not sure which phone you have. You might be able to swap it around. Might be usually at the bottom or the top.
It's just while I'm in the program is the weird thing.
Oh, it might not let you flip.
Yeah. Now I have to get out of this. Okay, I don't even know where I am anymore.
We can see you.
Yeah. Okay. So, okay. Get that out of the way. There we go. So that would be let's see, up.
So each one of these is an axis of rotation.
Well, let's consider them fractional charges. There's an up quark, has 2 fractional charges. There's a down, 1 negative fractional charge. Can we see those? I can't see the framing that well.
Yeah.
I'm guessing on the framing.
Yeah, no. Okay.
So there's the other, the down or whatever, the anti-down and the anti-up. So there's our 4 quark possibilities right there. Right? This is all you got. Up, down, anti-up, anti-down. So and then there's the weird generations too.
So the 2 crossed axes are basically that would basically have 2 of the color charges. So 2 of the color charges are there, and then you would have another color charge for there. So that would give us our 3 color charges, and then the others would be the anti-color charges.
Yeah. Okay, just don't get me started on the color charges.
Okay.
Because I think they're totally unnecessary. Really, I don't think that's
our interpretations. We might be confusing.
Yeah. That's cool. I understand. So, let's say you want to build a proton. Got 1 up, 2 ups, and a down. Right? 2 ups and a down.
Mm-hmm.
Okay, so I'm just going to take this one up and one down, and I'm going to squish them together and make them into a green one. Because this is a positive charge and this is a negative charge, so I'm going to turn it into a photon. Only it's a really tiny photon. So we'll call it a green one. And then we have 3 axes left over. Boom. There's a proton.
Nah.
There's a mass. There's the Higgs in the middle. Here's the 3 fractional charges, each of them oppositional to each other. Electrostatic charge, electric charge, magnetic charge. But an interesting thing that I thought of is this electrostatic, electric, magnetic relationship only goes one way. You can only go deeper, and then you have to come back out. You cannot create a static charge from any possible arrangement of magnetic positioning.
It's going to wind
Magnets
together
don't-
somehow.
Magnets have reconnection.
Mhm.
Electricity has reconnection. There's a battery, there's a positive and negative, and it's the flow, the reconnection through the wire that completes that. But electrostatic is the fundamental, because it's just expansion and contraction, outward and inwardness, that can't be created from anything else. It is the fundamental. You manipulate it by making it laminar and making it funneled through a tube, and you get the electric condition, where you have a laminar flow of charge. Then, if you take the laminar flow and you put it in a loop, and I just thought of it the other day, that when you make a loop, you're essentially creating a plane, which is why magnetic loops, when you coil wire to make a magnet, the turns, like if you have 1 turn on one side and 10 turns on the other, you've multiplied the voltage by 10 times. And it's like, oh yeah, well, that makes sense. But it's like, wait, why does that make sense? Only
Wait. By a factor of 10?
Yeah, that's the way transformers work. Like you want to, you've put 5 volts in on one side and you have 10 turns compared to 1 turn, you'll get 50 volts out on the other side, or vice versa, depending on which way you run it.
Now, Kali, this is a very naive question. Is that an effect of simply our human notation, or
No. This is just like, it's just the way it is. And
it literally is a factor of 10?
Well, it depends. No. It's exactly 1 to 1. Like, if you have 1 turn on one side, and you have 10 turns on the other side of your transformer, then you now have a multiplication of 10 or an inversion of 10, depending on which way you run the electricity.
Right. But I'm asking, do we engineer them that way? Because that seems to be an optimal.
Well, I mean, you could have it any number of turns you want, but the point is that the number of turns creates this ratio. And everyone just accepts that as like, oh yeah, well, yeah, you made a turn, so you get to multiply. It's like, why? Even if you have little skinny turns on one side and big fat turns on another, you can, like, it's not purely geometric. There's a weird, like, it's not about the amount of wire you used. It's about the number of turns. Like, why isn't it any of the other physical factors? Why is it only the number of turns is the factor?
That's a very interesting question.
And
do you have?
It relates to capacitors in the same way, that if you take a stack of plastic and metal and plastic and metal and plastic and metal and plastic and metal, conductor and insulator, conductor, insulator. When you apply, let's say I had a stack of 100 and I applied 100 volts across the entire thing. each section of that gets 1 volt. It's distributed across. And it's just this weird, like, it just seems this laminating thing is really, really, really fundamental, but it only goes the one way. It's like electrostatic. Curve folds into electric, folds into this, because we added a dimension each time. We had a point, we created a line, now we made a circle.
I'm just bringing. I clicked on the first thing that came up in Google when I typed in like voltage to rotation 10 to 1. I'm like setting up the conditions. Supply voltage, motor currents, armature resistance. I don't know what that is. Coil inductance, motor generated voltage. Oh, I really need to learn machines. I used to love cars and everything, but it was just like, let me just add together. That's not how the system works. You got to consider the system. That's one of the things that I learned. Angular velocity, transient waveforms. Okay. All right. That actually looks like a machine thing. Rotation. I see. I was when you said that transformers were set up with a 10 to 1 ratio. I'm like,
that was an arbitrary.
Oh, okay. See, I wasn't sure if that was an arbitrary thing or they were configured because that had a meaningful ratio because that wasn't optimized for some reason. Because I'm totally biased. I have reasons to believe why that could be true.
Right. Well, I mean, often you will have a simple ratio like 100 to 1, just because it's like, well, that's easy, or 1,000 to 1, you know, because that's like, okay, that's easy. That's the thing about Tesla coils too. Tesla coils only have like 2 turns on one part, 2 or 3 turns, like a very few turns at the base, and then you have this the tower that's like 1,000 turns or 2,000 turns, so you've got 1,000 times the voltage. Boop, right there. If you can get, you know.
It's no. I mean, charge is absolutely fascinating. It's like I did a little thing. I sent out like the little published notebook earlier. I still need to do a video on this, but I just looked at this and especially once you start getting familiar with some of these things, you start recognizing friends. I'm like, all right, Planck charge. I see these things, these expressions. It's like, all right, even the monastery, we have a slight deviation from that for our calculated number. I have reason to believe why.
You guys need to connect with. Oh my gosh, I'm so bad with names. But there's this posse on Twitter that have been doing their own like deep dive into just like, you know, geometric derivations and interconnections of these things and how it's like, wait, yeah, there's only one number. The number is the Planck number, and everything like is harmonic derivations and like basically like step downs from that, you know, sort of thing.
So that's a very interesting question. Okay, here's my question. Okay, so if we have measured, so to speak, because we technicalities aside, if we assume c is a unit, if we assume it is the speed of light in the vacuum, we go into this, and if we if we know the speed of light to 9 significant digits. We worked hard for those digits. All right, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. Okay.
Where was that measured?
According to some laboratory measurement, smart people, the moon maybe. I don't know. We put mirrors in. These are questions.
They subtracted Earth's gravity from that?
Holly, I don't know the answer. Again, these are great questions. Assuming this is okay, my question is: if we say we know this to 9 significant digits, okay, we know this to 9 significant digits, we confidently say that. So why is it that the blank?
I just think, did we measure it on the moon also?
I don't know. I think
have we measured the speed
maybe?
Have we measured it at ISIS in the International Space Station or something?
I think we have.
Wait, We measured it by shooting between the Earth and the Moon, didn't we? That's how we measure it. We bounce a
I
mirror
don't
off
know.
the Moon.
Sir, I know we've done that. Apparently, at least that's what I've been told. And I don't see. My question is, if
The
we know the speed of
laser on
light,
the Moon thing.
but if we know the speed of light to 9 significant digits, why do we only have, I don't know, like 4 here for the Planck time, and for the Planck length we have 5? Why don't we have confidence in them to 9 significant digits if it's just length divided by a unit of time?
Well, I mean, no, I think that's these. How are these?
See, that's the thing that makes me go, huh? What's going
No,
on here?
that's the
Why
thing.
is that?
These are derived, are they not, from things that were more precisely
We do
measured?
quantum
This is
mechanics. We arrange things in particular ways, and we get these units out.
yeah. But that's the thing. Like these are calculated. We haven't measured Planck units. They're too small to measure by a huge orders of
We measure the
magnitude.
Planck mass all the time. It's 10 to the negative 8. It's within, I think,
No.
micrograms.
But how
or
is
something
that
like
measured?
that.
How is that measured?
Oh no, we calculate it. It's not. It's yeah.
That's what I'm saying. So what have we measured? I think is through empirical evidence, we've measured EO and UO.
We measure constants of nature as we have defined them, and then we derive these from our measurements. So it's the sum total of. So it's whatever. So because some of these, it's like, what if this is based upon G? We only know G to maybe like 5 digits now or something like that, depending on who you ask. So it's like, that would make sense because
Right.
Big G is.
I mean, and we always need to remember we exist.
We have 4.
Even this gap between any planets in our solar system already exists in a significant gravity well. Already. Our solar system itself is a big gravity well. And then the galaxy only exists because it's a gravity well. Like it's a bunch of stuff falling down a hole. It's called a black hole. You know? Like
It's I mean, and then you're like, well, why is that a thing? It's like, I don't know. I watched some 3+1, 3 blue plus 1 brown videos, and it's like vortices, and it's like eddies of eddies, dispersing into more and more eddies, approximately about 1/3 each, and then they end up dissipating into viscosity. I'm like, oh, that kind of sounds like some heat or something like that. I'm like, wait a second, Kali, what were you just saying about like vertices and thirds and stuff like that? And I'm like, that's why I'm like, the whole vertex thing, I could see things bending in on each other and stuff like that. I could just see it being some form of a geometric structure and just kind of just like doing its thing. And depending on what we believe we are observing here with our measurements and stuff like that, it's like maybe there are other perspectives. Because if we're measuring the energy, it's like, all right, the energy of what? It's a boson. All right, cool. What does that mean? It's a boson. It has integer spin. Oh, that's a boson. It's like, okay, what's it doing? We got some stuff. What is the thing that it's doing?
That's the thing. Look at the data only is my suggestion to everybody. Try and back off a lot back to the data because people interpret things. Like even the whole electron spin. It's like, does this electron already have spin, or is the spin imposed on it? Like when you just fire a random electron and you're doing that experiment where you put it through a magnetic field and a bunch of them get diverted one way and a bunch of them get diverted another way, right? It's the big spin experiment thing for electrons. Now, those electrons, when they first are shot out, do they have a particular spin? Do we know that? I think it's been determined through quantum mechanics decision of like basically we don't know, so let's call it 50-50.
But I thought as soon as we measured, we start messing things up.
That's the thing. It's like it could
Oh
have
no! I no. See, I think they induced the spin. I think that's how it goes because I think they induced the spin,
That's
and
the
then
thing.
maybe
When
they
you
probably
apply-
measured that. I
Yeah.
think that's how they do it. I think that's a
but it
thing
is
that I
unitary
read.
spin. Great, but that means that basically, like as soon as you put a magnetic field on an electron, the electron basically all has to choose a plane to exist on because you just squished it with your magnetic field. And when it chooses a plane, just like a coin, it can end up heads up or tails up. Because this coin was spinning, the electron was spinning randomly in a undecided state. And then, you collapse the wave function by opposing that magnetic field and you squished it. And then you can play with it later. I'm pretty sure you can do like another squishy sideways just to confirm.
Now we assume Akali here. We assume a fair coin in this instance here because
we assume a fair coin, which is actually not true.
Which isn't even fair according to studies and when they did like a couple of, I saw that study. It's like according to our fair coin, our actual experimental, it's like that's off by about 1% there. It's like it seems to get heads there. I'm like, that's fascinating. Doesn't necessarily surprise me.
Tiny. It's a tiny percentage, as I recall. It's like not even a percent. I thought. It's like not even.
But it was enough where it's like it looks larger than error.
Yeah, you'll know.
Well, my thing is, I could flip a coin and it could land on its side there. That is a possibility. It's a statistically small possibility, but we never talk about that. I don't know. Is that a monopole? Rampant conjecture on my part. No idea. It's mostly a joke, or is it?
Yeah.
But no, well, that's a fun thing when you get to the okay.
Yeah, I think if they find a monopole, it will have to be a weirdly constructed monopole where there is the other pole, but it's just hidden. Like, because or
what if they were wrapped up together? What if it was just the folding of just two idealized tetrahedra into something that some may call a Giesking manifold? You double covered them, and then you get one falling into the other, but they're balanced together. Otherwise, they would basically just blip out of existence. See, I have no idea if that's the case. I take people because I heard Professor Edwin or somebody say, if one monopole exists, we could make Maxwell's equations more beautiful. I have no idea how that works in practice, but this is what I hear smart people say. So I'm like, what if there were two of them? And that's the cinching point of our realm of persistence. And then we can make Maxwell's equations more beautiful. I'm doing that out of a completely self-interested. I just want the equations to be easier so I don't have to think about them more.
All they need to do is allow true inflow and outflow. That's all that needs to happen. Because if you designate a volume and that volume can't change because they're always using these incompressible fluids and crap. Okay, because the volume can't change, all you could have is flows. But you can't have.
I'm totally all right with that. I personally support that. I agree.
But when you have a flow in a closed volume, you can only have reconnection. There's not a reconnection in a closed space. And charge defies that, in my opinion. Charge is monopole. Like a proton has the electron, but the electron's all distributed around. It's not really statistically, like, oh no, it's a particle. It's a particle that gets to move at infinite speed.
Well, occasionally it appears to be going through the proton. Don't that just be it all?
Yeah, exactly. So, come on.
Hey, Barris, thank you for joining us, my friend. No, hey, thank you for sharing that video earlier. That's cool. No, here's the thing. I've been immersed in this, but I always got to realize it's like there are a lot of folks out there that maybe they're kind of just starting getting into this. It's like, oh, who the heck is this random dude? Should I assume everybody is watching? No, of course somebody's like, I haven't watched all my own content and stuff like that. So every once in a while, there happens to be some things that kind of like, this seems to be an explanation. Oh, I am aware of some other material that was, I don't know, out there 11 years ago that I am aware of. Let me overlay this together in an interesting way. And anytime I can use Magic Carpet Ride from Steppenwolf is totally a plus. I'll do it. But basically put together in a fun way that some folks might look at and might go, that's interesting. And if it helps them out or leads them down a path of interest, cool. I mean, it's I'm literally a freaking monk at the place called the Physics Monastery. But I'm a crazy person too.
Right.
I'm sorry, Kali. I was interjecting.
No, but because you're the you guys are the figure 8 knot. So my rebut is there's an antimatter universe and a matter universe. And what is the what's this term you guys use about the where you turn something inside out thing, the space that's
Inversion.
not the same? That thing.
Mm-hmm.
Of a trefoil knot. What is the anti of a trefoil knot?
That's a good question. I don't know.
I'll tell you, it's the trefoil knot.
Okay.
Just the same way that the antimatter universe is the inversion of the matter universe. And the same way that Shirley's surface is made out of a trefoil knot. Just saying.
It's no.
I love this battle. It's
well, number one, I don't know the answer. Number two,
I know, but this geometric thing is like really like teasing me.
No. Because here's what Kali, I actually have reason to believe that. That's why I said in neutron. I believe at least some of the mechanism for neutron decay cosmology looks like evidence. I think it might be right. Yeah, that's what I'm believing. And the reason I believe that is because at one point Thad was going through some of like the animations, and basically we end up like seeing two trefoils, and it's like we don't necessarily know what they're doing. I think Thad may have a suspicion that particles as we know it, I'm not sure I necessarily agree with that on this, but this would explain a lot. I think I'm probably getting this wrong, is to answer the question of where is all the antimatter? I've heard Thad use the expression, it's kind of like if you're paddling in a lake, if you're in a canoe, if you're moving that oar, you're going to create vortices that will go in different directions. So if those come together, I'm like, with what you have been saying, I'm like, well, what if those vortices, they turn in to trefoil tangles, but they would need to come together, and when they come together, you get something like the complement of the figure 8 knot. Like now you're literally you're taking two knots and increasing it by like a genus or something. I don't know if that makes any sense at all, but that's kind of the vibe I'm getting.
Well, yeah, did you read also, interesting thing, the trefoil, I'm pretty sure, if you run velocity through the trefoil knot, like if you could laminate a flow through a trefoil knot, using Bernoulli's principle, it would therefore self-constrict into nothingness. And recently they built the very smallest knot ever, which is, I'm pretty sure, some sulfur.
Yeah, I think it was gold atoms. No, I think it was gold atoms.
Was it gold atoms?
It ended up, once they got it, it self-assembled into a trefoil knot.
Come on.
I saw that. I'm like, oh my God, I got to share this with Kali because it popped up. I'm like, well, that's a beautiful thing. And I'm like, well, that's basically kind of Kali's thing. So I'm like, let me share this. It's like, that's an observation. It's like, what do you say to that? It's like, that's the thing. I'm looking to see like what makes sense and everything. It's like, I could be totally wrong about freaking everything. That's a possibility. I'm just kind of following the evidence this way. And if I hear different things, I'm like, well, this person's been talking about this for a while. Maybe there's something to this. Let me look into it. I mean, that was fascinating. Oh, trefoil knot. think it was gold atoms. Let me see.
Right? Yeah, and it's like crushes itself, just like where. And who knows? Like, actually, didn't they develop that as part of a? They were making new catalyst surfaces and stuff like that because micro gold particles are really good for that because those little gaps in all the weird shapes are smooth surfaces to fit, sort of like help fit things together into, I guess. I don't know. I've never really explored the charged surface of these gold molecules.
I will accept cookies for everyone. All right, the tightest knot ever is made. A tied up chain, 54 atoms long. Tiny molecular chain of gold, carbon, and phosphorus. I stand corrected. It's tied itself up into the smallest and tightest knot ever seen. Okay, I don't think it's not an actual picture. Knot made from gold crosses over itself 3 times, known as a trefoil knot. The tiniest and tightest knot ever made. The knot contains just 54 atoms, including 6 gold atoms that form its backbone. Help us understand knots, blah, blah. Oh, is that it? Oh, that was terrible.
And there was a recent development on fullerenes, too. I can't remember. I think they stuck a fluoride atom inside of a fuller cage, like a fullerene cage. And when you do that, I can't remember what happened, but something weird happened because of the way that the charge acted once it's got caged like that. Because a fluorine's got this like super, what's a fluorine? Is that it's just missing 1 electron?
But before we jump to that, this is the part that I love. It's like, yes, the gold 6. It's like, however, is made differently. And Pudafat told new scientists it was an accident. They were mixing 2 liquids containing different molecules to make a structure interlinked but not a change called catenanes. Yes, using X-ray crystallography to study the product, they found some of the catalytes had self-assembled into trefoil knots. Oh, that was beautiful.
Path of least action.
We were talking about fullerenes.
Path of least action, because it's like that again. A tight trefoil knot means that each strand is always 90 degrees to the other 2 strands. It's just it's a geometry thing. If you make a very tight trefoil knot, like if you could, go to Wolfram, cough up a trefoil, and then like we make it so we can adjust it. Can it do that? I could probably look it up. I don't think I can make that tight a one on my GeoCalc. I don't know. I should be able to.
So we could do that. Can embiggen it.
But if we could like tighten it. But even if you just look at that right now, if we look at a 3D, you'll notice that each of the strands at any moment, like each of the 3 loops, any given point, like let's look at the furthest out point, one of the furthest out points there.
It has symmetry. Hold on, let me do this.
That's the thing. And the symmetry means that all parts of it are 90 degrees to another. It's like oppositional part nearby.
So it would have maximum fluid. That's like one of the reasons they do it.
It's self-constricting. Yeah, because of that, it's self-constricting. Because each field is like pulling in.
But if it self-constricts too much, like what happens?
Well, until it's stable, until it touches itself, I guess.
Would it keep flowing, or would that kind of like put? I don't know.
No, I think that then it would be stabilized because then the surface of the one strand would be contributing the same way that there's a model of neutrons, of nuclei, where the protons stay protonized and localized, but the neutrons in this model, and this is you could read it someplace, but it's more like the neutrons form a soup around helping distribute the negative chargedness to all of those protons to satisfy them, which is why you always have to have more neutrons than protons, because you have to envelop the protons, except for the external protons, like all the internal neutralized protons sort of thing, like the only neutrons that count are the protons that count are the ones on the outside, right? All the other ones sort of get stabilized into these nice, neat electron shells that we hardly touch. What do they call them? The valence electrons, right? There's the valence electrons, which are the active electrons, and then all the other electrons, for the most part, are just layers of charge very close to the nucleus, right? And fairly stable and not that active, and they don't interact in chemical reactions. So all of
I
those
still need to
ones,
do the deep dive on viscosity. Sorry, no, I'm talking about the Reynolds number that
yeah.
treats the triple.
Well, that's the thing.
Oh, but
EO, I
190,
just see EO and UO, like permittivity and permeability, as like weird expressions of the Reynolds number of space, because that's what gives us C, and C is sort of like, oh, that's got to do with the Reynolds number of like the curl that you can have.
Well, we go to it doesn't come down to the question. It's like, is there actually a zero, or whatever the actual? Can we actually achieve zero? Like, is that a thing? And if it's not a thing, then well.
Okay, look at Jonathan Gerard's output recently, where he was doing these things, and I'm like, hey, why is there a big bubble of like, there's no graph there at all, and then there's a ring of really, 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 really dense graph, but it's like around a hole. There's a hole there. There's like nothing there, which is in the middle of a singularity. As I say, it's like, to me, it's like there's the surface. There's the surface. It stops there. It's a big singular surface. And I think it's our conception of singular is like bad. And I did a video trying to communicate it well, but it's like, okay, it's singular, which means that you affect any one part of it and all of it gets affected. It's like you're playing one of those tile shift games, and it's like, well, you want your tile to move, but that means that every other move on every other tile on the entire screen has to move too.
Kali, how dare you assume thermodynamics within a system? I mean, it's okay. We pop over to Jonathan's stuff here, and I'm like, all right, yeah.
Okay, and then this. Look at over those other ones though. That's one I don't know what that is, but look at those other two. Those other all that. What's that? What's that?
Oh,
those are
that's very
perforations.
interesting. Oh yeah.
What happens there exactly? What happens to the data? What happens to the information? What is that exactly?
I think those are two inspiring small black holes. I think that's what it's supposed to be. It's like, all right, they're kind of coming together, starting to come together here. The pressure, the bubbles are going there. The bubbles are actually all right. Oh, the event horizons are kissing. Oh, look, they kind of right there. It's like, oh, look, oh, it goes circle, blah blah blah, starts to rephrase and stuff like that. And it's as soon as he said he could start to trace the data.
Brownian, yeah, I dropped the link of this Brownian paper that I was reading about in the chat.
You want to know how I can tell Jonathan is he's a true scientist? It's when I just see a post like this, I set aside a day for paper writing. It's now 4 p.m. I've typed up one short proof, written one paragraph, which I hate. And I've spent the last half an hour yelling into a plastic cup and listening to the different reverberation effects from various angles. I'm like, that man is a scientist.
Right? Oh my God.
I just see that. I'm like, it's so true. It's so true. You're trying to get a feel for what's going on. He's doing oscillations. He's trying to get a physicalized thing because he's like a mathematician. So he's like, I'm trying to get a physical feel for like what the heck is actually going on. Power to him.
Right? Yeah. Yeah, I wonder if you could make. I'm so curious about how crazy it's going to get when we get good at metamaterials, because I'm pretty sure it's like you could make passive, all kinds of weird passive things that set up passive fields. It's like the scalar field or that weird Bohm, uh, Aharonov-Bohm effect
Oh, the
thing.
Baramod Bohm radiation. Isn't that kind of like going to like someone like the unrough thing? It's the heck is that? The Bohm thing. It's I remember hearing all these things. I'll kind of listen to it, grok it, read it. I'm like, all right, there's some stuff doing a thing, and try to conceptualize it the best I can, and be like, all right, if I need this again, I'll be able to look it up.
Right.
Oh.
So the gist of it is though that somehow, let's say you have a magnet, right? And now we're going to take that magnet and we're going to put a copper pipe on top of the magnet, which is going to totally close off all in theory, we're going to eliminate all magnetic field by doing that because it'll all reconnect. And you can go around with a device and try and measure magnetic field, and you will feel it will measure no magnetic field by all of the devices that we generally use right now. Yet, if you ran a signal down the two sides of that magnet, one of those signals would be phase slowed by the existence of that magnet, even though we've shielded the magnet as best we possibly can. That there's an alteration to an aspect of space-time that is not impeded by that copper. That's a kind of stress on the space-time continuum that doesn't get blocked the same way. It's almost like charge is one component and the flow of that charge is a completely separate dimension almost. That it
And
can step aside.
no. Sorry to cut you off. No, it's fascinating because that's. I remember what was it? It was blah 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 blah. Oh, what was his name? What was his name? No, it wasn't Eric Dollard. It was Eric Dollard. He was big because he worked for like RCA back in the day. And according to him, they would go out there, they would measure these things, and there would literally be times where it's like there is no detection of any of this at all. It seems to disappear. They called it not transient space. They called it counter space. Counter space was what they used. Hey, Jen. But no, it was really fascinating. You look, I'm like,
I
I
think
hear these folks saying about this.
Thomas
Go on.
Bearden, who is considered like totally like quack by many people, but whatever. He thinks at least he thinks outside the box, and you can't envision something until you're like, it's got to be a dream first, and then we materialize it from there, right? You condense it
That's how
from the
Dick Feynman
vision.
pictured like super fluidity. He's like, I had a dream. I was too afraid to tell anyone for like 20 years until actually they discovered it.
Right? Yeah, exactly. So,
Because it seems crazy.
Where were we?
We were talking crazy, and something needed to be dreamt before you could actually like try to like actually put it in. Like, I don't know. We're talking about the Aronov.
Hi everyone,
Bohm.
nice to see
One
you
step before
both.
that. Hey.
Oh, the Aronov Bohm. Yeah, this thingy. Hold on, where are we at?
Oh yeah, Thomas
Aronov Bohm
Bearden.
effect.
He called it
Thomas
Bearden. Oh yeah, that's the Aharonov Bohm. Yeah, they might have a good diagram there. Because I always find the diagrams are most sort of salient. Oh yeah, that's
I don't know what.
Go up that.
The one there.
That one there. Zoom in on that.
Okay.
So basically, this says because of the theoretical rotation-y part of the electric current that created the magnetic field, right? Like you make the coils to make the magnetic field. The magnetic field is conceptually a bunch of current flowing in closed loops all the same way, which therefore creates a chiral
The claim is gravity has a non-trivial effect on a charged particle.
Yeah. Gravity's still like c² thing, you know.
Still a thing.
Okay. Yeah, this is nowhere near strong enough a magnetic field to be causing any kind of gravitational effect.
Well, I just think it's interesting. Parrish is saying that apparently some of the James Webb, some new pictures there, it looks like they're detecting. It looks like braided plasma filaments. So I haven't seen that yet. That's pretty cool. I mean, I have no idea. It's just a fascinating time to be the observer. I claim.
Yes.
Oh.
Definitely.
Okay, sorry. Let me bring that back.
Yeah, so has it like conclusively disproven the Big Bang or what?
All right, Eric Lerner.
No, but come on.
I'm sorry.
I'm pretty sure that first they detected all these galaxies in the early, quote unquote, early universe that were weirdly shaped, like really weird oblongs and stuff. Yeah, and then all of a sudden they got better resolution on them, and it's like, oh dang, those are barred spiral galaxies at 200,000 years old. That shouldn't happen yet, you know?
Yeah, it's almost like the idea of the universe having a beginning is self-refuting.
Right? Like, I'm sorry.
I don't know.
How do you have a first cause? I'm sorry. It's like
it's actually self-refuting because for causes to happen, there has to be a substrate.
There's cause,
and the substrate is not cause. It's the thing that allows for causes to happen.
I guess. Ooh. It seems to me there's only causes. It's just like endless causality in every direction as far as the eye can see.
Well, I would agree with you.
Ladies. I have been on internet record as making the bold claim that T is greater than 14 billion. There, I said it.
Well, how about just reject the notion that that a finite age to the universe is, just reject that idea.
Yeah, what did my brother say?
I'll start off by going to a closer whole number and saying it's greater than what people are saying. I'll take my incremental victories.
Well, there's no evidence for the Big Bang, right?
My brother had this take, and he's just like, well, it's like, it doesn't matter how long anything is. As soon as you compare it to infinity, it's like, it's nothing. Like there is no time. There's only now, because everything's got to be so thin compared to everything. It's so big.
That's my terminology. I think is important.
It's like scale reduces as soon as you've got infinite. Scale is completely a weird even idea almost.
Scale is a finite concept.
Yeah, it's so local.
Whoa, I don't think I've ever actually heard that before. Okay, continue.
Well, basically, what's being said here is that, like the gap between any finite number, if you think of the biggest finite number you can think of, the gap between that and infinity is infinity, in short. So you're talking about an essentially insurmountable gap.
I prefer to take a localized realm-based perspective and tend to agree with Professor Weilberger in saying that I don't believe in the real numbers.
Well, what does it make doesn't make sense to believe in numbers, because if you're basing your views on empiricism, there's no empirical evidence of numbers. So, and people, are like, that makes no sense. It's like, where's your empirical
Jen, what did the number 2 ever do to you?
Well, I mean,
Elmo's going to be in for a hard time now.
The numbers are good because they don't exist. What exists is confusing. Numbers are
they're useful. They're useful ideas. I'll agree with that.
If you take the notion of an ordering principle, that's normally mixed up with causality. An ordering principle minus a causal principle, that's numbers. Because numbers don't have any causal entailments. They're just really structure.
Oh, this is getting hot. Welcome, Brad.
Hey, what's going on? Can you guys hear me?
We're just talking about how numbers aren't real.
That's weird.
It doesn't even make sense to think of numbers as real, because Like if you're going to say something's real, you could say like matter, and that would then you'd be a materialist. You'd be. I'm not saying we should argue that.
We're
I'm
at the
just saying
edge
like,
of metaphysics.
that makes sense. That makes sense to say that you believe matter exists, because then you can say, well, I've got a pencil here. It's matter. I have a basis to believe it exists because I'm perceiving it. Okay, that's basically the argument. Where's the equivalent argument with numbers? Not saying they're not useful. We're not talking about utility. We're talking about existence, which is ontology. That's a separate question from utility.
Well, but this comes down to, I think, use of language, right? Because if you see two baseballs and you want to describe it, you can say, I believe in this baseball, just like you're saying. But you say, I got two baseballs.
Mm-hmm. So the baseball doesn't exist, though. You wouldn't say you believe, like no one's a baseball
it's matter.
realist.
It's matter. You're looking at a baseball.
Yeah, so you're not saying the baseball is real. You're saying the matter that makes up the baseball is real.
All right, but I got two of them.
But you don't have two matter. You have matter. Period.
I
like both baseballs are constitutive of matter or comprised of matter. I'm not sure how to say that exactly, but what makes up both baseballs is matter. So the fact that there being two of them, that could just be something that your perception has endowed. So
okay, but I mean, just like for language, right?
To say that two exists, because I think we're on the same page that if we're on board with this metaphysical aesthetic, then we can say matter exists when we're talking about a baseball. But how then can we say that two exists?
Are we discussing within the physical realm?
Well, the idea is that two is not something we can point to as existing. Two is something we can point to as a model that makes it easier
more of a
to
Platonic
understand.
conceptual framework, I think.
It's a model that makes it easier to understand what exists. How old am I? Well, I went around the sun, then 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 I went around the sun. Nobody wants to sit around for that entire, you know what I'm saying? So you just compress it to a symbol.
Do we want to speak in a realm where numbers are a useful idea?
We don't want to make the mistake. We're not going to have useful stuff if we don't understand the metaphysics. And if we think that something is real just because it's useful, we're not going to understand the metaphysics. So does everyone understand the point that to say that matter exists because there's a baseball is not, it's at very least not the same thing as saying that two exists because there's two baseballs, that those are different categories of existence, because one is direct perceptual and one is meta-perceptual. I'm sorry, I keep forgetting how to pronounce your name.
I should have mentioned there was a 2-drink minimum coming in. I'm just playing.
Is it Callie or Kaylee? I'm sorry, it's Callie, right?
Callie.
Yeah, there you go. Okay, I got it. Go. What were you going to say, Callie?
So just to help with this, like sort of in Irish, it's sort of like there's a connotation around this where it's like, okay, there's a baseball, right? Sorry, what's your name? The new joiner? I haven't met you before. Brad.
Yeah. B-R-A-D.
Yeah, Brad.
He popped in right as we were finishing, I think, episode like 4 or something like that.
Yeah. No, we just haven't chatted like long. Don't have a report, but okay, there's a baseball, and it has a range of attributes, this baseball, that we all recognize as being baseballish attributes, right? And then you have another baseball. Now, you can say there are two baseballs, but we know, in fact, there's a gazillion baseballs.
Okay.
What we are saying is that there is a baseball, and there is this other thing that shares very similar qualities. So we're going to call it a baseball. And because there's a baseball here and a baseball there, we have this thing where we devise numbers so that when we have a limited amount of the unlimited supply of things that we don't even know how much it might be, and we only have a limited number on hand, and we want to itemize them, we've got this schema where we give ordinals to these objects, and it wouldn't matter that they are similar or not similar, because sometimes we decide we're going to say baseballs, and because they possess these things, these attributes, we're going to say these are 5 baseballs because the things that we've decided have enough attributes to be decided as baseballs out of all the matter in the universe and all the baseballs in the world, because these are all the ones we see right here. So here the baseballs that are available to me, I will measure them in that ordinal way that we have. And so I will say, this one is a baseball, this one is a baseball. You might disagree which ones are baseballs and which ones are not. But if we all agree, then we'll probably come to the same conclusion about the local number of baseballs in the vicinity. But that's only because we gave this like ordinality to this matter that happens to have certain attributes. Now, you have objects that are indistinct or like cross boundaries between things. You have a baseball, but it's like got a weird stitching on it. Do you still consider it a baseball or not? These become ontological decisions that we decide arbitrarily in case and this and that. So I think this is what it comes like. This is where I think, Jen, and you can correct me after this, but just sort of like we're just trying to make a distinction between this device that we've created called like numbers and and as a useful tool, when really what we have is an immense continuity of stuff that we can organize according to various attributes if we choose to, and that has to do with our perceptions of things and all kinds of complications like that, because we can consider a bunch of people. These are people, but that's not a person. This is a person, whatever. These are personal decisions we make. But just that distinction about numbers don't pre-exist. We had to create this device that we find very handy.
For sure.
That they didn't exist pre anything. That they exist through a device of our configuration, basically.
It's language. I mean, I think.
But hang on, just pause for a second. You understand that the apple, there's a sense in which not the apple, sorry, there's a sense in which the baseball is language independent. And it's the sense in which it is matter.
And it has attributes.
Well, but the thing is for our consciousness.
Because if you're just going to say everything is, if you're going to say everything is a construct. Yeah, but if you're going to say everything's a construct, one and baseball are both constructs. It's just that the one isn't rooted empirically. The baseball is. So they're different kinds of constructs, and if we confuse them together, we're going to end up with metaphysical flattening, and that will have problems later on because logic comes from metaphysics. And if you flatten your metaphysics, your causality is not going to actually reflect your system. Are you completely confused? I can try an easier way.
I can try and totally understand that, but I just think it's important. I just don't see a lot of like moral significance or I don't. I think when we perceive what we perceive, right? You call it reality if you want, but when we're trying to essentially language, I mean, there's sort of a kind of duality or a reciprocity. But I think language is our attempt to communicate, assimilate, record, and understand reality. And to the extent that in order to do that, we have, you can say found it useful, but, we've assigned numbers to like, or
Kylie,
our language embraces numbers.
Back a little bit. Sorry.
Our language, we develop numbers because they're useful in communicating that reality. I think that's fairly not uncontroversial. Uncontroversial.
Nobody would take issue with that. Now we're on a conversation about ontological substance. So that's what exists beyond like causality exists in the universe. We are causal beings, therefore we can have models for causality. And we want to know what actually of these models is the most reasonable. So if I was going to say matter exists because baseballs exist versus two exists because I can see two baseballs, the second argument is less grounded in empiricism.
I believe in baseballs.
Does that make any sense? Or like was that clear?
Empirical implies observation, right? Because empirical reality
Right.
is essentially based on an assessment. Like, it's empirically there are
slightly
two
different.
baseballs,
Okay,
right?
you have to,
I mean, there's
you have to
no
understand something. In science, empirical means something different than philosophy. In philosophy, empirical means that which can be verified with the senses. In science, empirical means that which can be verified
measured.
by the senses to have been replicable under the conditions stated. So it's
It's just
very,
measured,
very
right?
different understanding of what empirical is. Now, I'm using an understanding that includes both. So I'd have to
Right,
know
but
more
you
about
could
how you're
if you had
referencing
two
empiricism.
baseballs and you measured, if you had two balls, it
Yes.
would be valid for you to say I have two, because you could
No,
you could measure them.
not ontologically, because my measurement systems aren't ontologically validated. Measurement systems aren't ontologically validated because we can't disentangle the effect of the measurement system from the observation. So
Can
that's
we
out.
count?
We can count. That doesn't mean that numbers exist.
Okay.
So it's two different kinds of questions. One is, like, the problem with modern Western philosophy is they tend to conflate the necessary conditions for rationality and the necessary conditions ontologically. Those aren't the same things. We may have necessary conditions for communicating, but the universe doesn't necessarily share those conditions. So we say numbers are necessary to communicate physics, but the universe doesn't necessarily agree on that. It may not need numbers, is my point, but it needs something.
Oh, okay.
Something
No,
we
no,
may not be
I'm
able to
saying
understand.
if we could kind of massage that out, I think it would be a fairly reasonable thing to say that numbers are a useful thing for at least our generalized current state of being and purposes, or
I mean, I don't know if
useful
if
things.
if we use numbers to, compute, trajectories of rockets and re-entry vectors and all kinds of things like that, it just seems
Numbers
to me
are a
to
model
say
for
that-
proportionality. You could use any
Yeah.
number system to describe that proportionality. All you're
Well-
capturing is proportionality. Okay,
Yes,
so
I mean, but I'm just saying
you're
that
saying the numbers that
the
capture the
universe seems to
proportionality
work
are
in numbers.
real. It does work, but you could use any number system to describe proportionality. You could use binary, you could use hexadecimal. It doesn't matter, because your proportionality would be preserved, because what's important is the amount of mass in your interaction.
Oh, we
The
were
result of
assuming
you're saying
number
it's not
systems.
real,
Okay, I
right?
don't.
You're not. I
Oh.
mean, just because it's fungible doesn't mean it's not real, right? I mean, because you're saying that you could use
you
any
have to
system.
establish criteria you have to establish criteria for what
No, you
makes
don't.
something real.
No, you don't.
If you're going to
I
talk
mean, it's
about
just
what
like if
makes
you want
something real,
if you want to
you
head
have
to the
talk
North
about
Pole, you don't
what
have to
those
triangulate your
criteria are.
position. You just put the rising sun on your right shoulder and walk. Right?
That's
You don't have to-
analogous, though. We're talking about a definition that is necessary to proceed, because you're saying that's not real. You have to you have to say what it means for something to be real.
I don't know. I mean, I think there are people who would agree with that, but I think just like,
Sure.
just like if you wanted to go to the North
one
Pole,
could be arbitrary,
you don't
so to
have
speak,
to-
but once you
Okay, go
define
ahead.
something, you need to build everything else upon what you defined. I think that's kind of the gist.
Yeah, but I mean, I'm just saying though,
I'm not actually
I
saying
think,
that. I think he's missed a deeper point, and I don't want to leave him behind in the conversation. So I'm staying on what may be a rather beginner level point, because he's just not initiated into this way of thinking, and a lot of people, even philosophers, don't understand this. Like, this is the empirical ontology gap. Well, it's look it up, empirical ontology gap. I guarantee you, people don't even know what it is, because they don't even understand the subject matter well enough to understand what's wrong with it. So obviously there's issues, but
Google that up, memes.
What about the notion of, like, whether something is true depends on how you define the word? Do you agree with that?
yeah, I think it's fair. Sure.
Right. So in philosophy, we're basically defining words so that we understand reality the best way as possible. So why would we start with numbers? So the idea that Memes said earlier, that is true in my system, that if you're going to build something, you start with your first presupposition, and then your next presupposition has to accord with your first one. So you start with, let's say, a causal principle. Or say we're going to do physics. We need a causal principle. And then within that causal principle, we can affirm some other things. Okay, the causal principle manifests this way and then that way through these vectors and whatnot.
Okay.
That's all consequent to how I defined it. I didn't have to define causality is my necessary condition for physics, but if I hadn't, physics wouldn't work. Because the thing we
Jennifer
call
is
physics,
taking
the
a
thing we
perspective
understand-
of literally if there was absolutely basically take all the existing stuff and things and basically how would you build a conceptualization from the ground up? That's basically what Jennifer's doing.
Well, I think that's a fair way of constructing your your paradigm. I think that's a fair way to do it, but I don't think that's necessary. I mean, I don't think that's the only way to do it.
It's not necessary, and it's not the only way to do it.
Sure.
I didn't say any of those things.
For reference, Jen, I think this might be helpful. For reference, Brad is essentially trying to build an basically you're looking to get funding to basically
no, I actually don't need it. I don't need it, but
okay.
I'm gonna. I mean, eventually I'm gonna, but I don't need it.
I'm just saying you're coming from like a heavy engineering where it's like for you it's like if I didn't have numbers right now I'd be screwed.
Well,
I'm just trying to give like a reference frame.
By the way, in my worldview, in the engineering, you use numbers. You can use any numbers you want. They just don't have an ontological reality. You know, you don't have to. We're talking about models being useful. That's the whole idea. You don't have to use ontological reality in your models, but your models will be better if you understand the basic principles of how ontological reality functions.
Everyone loves a good story.
And one such principle is that we don't have empirical evidence for numbers, even though it really seems like numbers are real. Like think about the periodic table. I could start with the periodic table and make a very compelling argument that numbers are real. But I would not even agree with the argument. Because that's not how I establish realness.
Yeah, I'm not a philosopher. So
the machine. So the machine. Okay, how does this thing work?
What's that?
Shift.
She's asking about your drive system.
Oh, yeah,
gears,
sure. We haven't had an update in a while.
Yeah,
So are these working on? Okay, are we working on electrostatic kind of Byfield Brown effect? Are you working on a more like rotational? What is that guy that was obsessed with the gyroscopic thing?
No, it's not that. Well, I'll tell you. Okay, so I'll just tell you I'll tell you how from soup to nuts how I.
Sorry, Jen. He's got a toy.
What's that?
Like, sorry, Jen. To get off of philosophy, he has a toy.
It's true. I've seen it.
See?
Yeah. No. Yeah. So, well, let's not. Well, Jen, let's make sure Jen was through because I don't know. Are you done? I don't want to be rude and cut you off.
I just don't know. It's like, are we really like? I think we've agreed that like numbers are just a thing that we construct as a tool.
Yep. Just like language, right? Just like language.
Only numbers are of a different nature because red is a physical characteristic that people perceive directly through their senses.
Sure.
All the characteristics of a baseball that we generally use to describe a baseball and make a baseball distinct from other objects are the kinds of things which are like about the matter itself and the nature of the matter and the way that matter is put together structurally. One, or any numerological stuff, is of a metaphysical, a completely different kind of ontological nature because you can never pull the oneness out or put the oneness onto something else, if you know what I mean. You know? It's not attributable in the same way that physical things attributes are. The oneness of something, I can like all I have to do is put another thing beside it and I just dismantled oneness. There's no oneness anymore. There's only two.
Okay.
You know? And that oneness is sort of like a very localized thing. As I said, it's like, well, we don't know how many baseballs there are. It's like one baseball. Well, I guess this is one baseball out of how many? What? Is there just baseballness, really? And this is a piece of baseball? And
Yeah, I
baseball
don't know.
baseballs come in quantized unit. What about if it's made out of foam? Is it still a baseball?
Yeah, no,
Now,
I mean, definitely.
now it's a foam baseball. But that oneness, because it will share attributes like whiteness and the way the stitching is designed and
sure.
stuff like that.
Size, weight.
Whereas the oneness is a very, very different kind of attribute we impose on things structurally that's not inherent to the object itself. Because as soon as you're someplace else, somebody can give you another baseball and you'll say, oh, one baseball. It's like, wait, how could that be one baseball when that was one baseball?
Yeah, sure. Yeah.
If you just like there's a very different sense of the nature of those qualities.
I
That
was
one
just
is
trying to bring him up to
experiential.
speed on the conversation, which was about physics and where do we start with physics?
Where do we
just
start?
so we can stick on what is the real of things rather than a number being this or that about something,
Yeah, I just think it arises all out of language, I know some people are sentimental about this is a number and that's what that is, but I just think it's language's attempt. It's our attempt to, describe, record, quantify, justify whatever our experience is. We use language to do it. And I think you can parse it and you can say
Do
this
you
is
use
that.
language to play Tetris?
When I think in a language, and
so you think in a language to play Tetris, really?
Yeah, I'm like, okay, I got to spin this here, and then
some people think in words.
It would seem that that's not.
I mean, I think I do. I mean, I think language.
Your experience on the entirety of everybody else is one of the big mistakes.
No, you asked me. I gave you the answer to the question you asked. You said, "Do you think when you?"
Well, the idea is that you're supposed to put an argument forward and then justify it, not just state how you feel.
I'm not arguing. I just answered your question. You just asked me if I thought, "Do I play?"
Oh no! He wasn't doing it. No, my stepbrother stuff thinks in words. This is the thing. It's like we all actually have like different computational ways. It's kind of like if we can't agree on like what color the dress is, like that was the point where I'm like, huh. Maybe we compute things differently and everything. So like that's why like the different perspectives and everything kind of like makes sense. I understand conceptually. I think we're just kind of like we're off kind of in the platonic realm and stuff. I'm curious about like Jen, like kind of like getting us that starting point for physics, and then if Brad could kind of talk about shiny toys.
Sure.
Well, you
sure,
need
whatever.
that's
my personal.
Yeah, I think you need a causal principle. For starters, that's where you need to start with physics is the causal principle. So causal
Don't mind
closure.
me, I'm eating pizza.
Everything is cause.
Okay.
So that would be a necessary condition for physics. And other than that, you would need a matter boundary that accounted for all of the mechanical motion that was observable.
Okay.
None of that's numbers. And that doesn't actually speak to ontological reality either. It's necessary conditions for us understanding ontological reality in the way that we can, which is through physics.
But when you think about like a causal principle, are you talking about like what, entropy?
A causal principle is the idea that anything that is observed was caused.
Okay.
So things are never imminent if they're non-caused.
Okay.
So in other words, like if something happens, it's possible to say why on a mechanical basis. So if you drop a pencil, you can appeal to some physics to say why it fell.
Okay.
Yeah, so that's a causal principle. It's the idea that there's no breaks in what's happening. And then the other one is a boundary through which you can establish mechanical motion, which is what physics essentially reduces to. So the boundary is between non-motion and motion. And you just have to set that up so that it makes sense. So that when you get to the part where it actually makes sense to add numbers to your understanding, which is when you're actually observing things, that your numbers are as good as they can be.
So you're talking about space?
Well, space is something that's observable, and then there's other stuff that's observable too. So it's mainly about understanding what does it mean for something to be observed.
Is space observable at all? Actually, I'd say space is the only unobservable.
I think
emptiness is unobservable. Emptiness is unobservable, and space
only matter is observable.
Space is a lot like emptiness, and emptiness is not observable, but space is observable. Now, whether you want it, you can say that that's you're indirectly observing space, so it's not really observing space. Like, I don't want to get into that because space is emergent in this worldview. So this worldview says that space, time, temperature, mass, and charge, those observations all happen at the exact same, not time, but moment. They co-arise. So matter is the thing that causes these 5 observations to co-arise. So understanding that makes all your other observations that involve these 5 basic primitives, they're not going to be self-refuting. Because if you're presupposing that temperature is independent from space or whatever, then you're not going to actually understand what's happening, what can be established empirically to be happening, which is a minimum energy solution. Because for things to be separate involves energy, and energy is minimized. And so therefore, everything observable is always observed. And only 5 things that I just listed are observable through matter.
So stuff requires things.
Charge, though, isn't necessarily observable through matter. Charge is
well, it is. That's what electricity is.
Well, but it's not the matter you're observing, though, right?
We're observing surface effects to her understanding, or my understanding.
I mean, because there's force, right? There's attraction. That's not observable, but it's measurable.
You yourself aren't observing electrical charge, but electrical charge is the observation that leads to you observing whatever.
I think we do.
I would disagree. Back when we used to have spare helium for balloons, we got to rub that stuff on our heads and discharge it on other people.
No, but you're always observing
without consent.
You're always observing the behavior of matter and inferring from the behavior of matter something.
Charge is smell. We detect charge on the hologram through our sense of smell. All charge neutral odor, everything that's charge neutral is odorless. Methane, oxygen, O2, N2, CO2.
Yeah, it's the polar configurations that definitely drive smell, right?
Guaranteed. Charge, sense of smell, we detect charge.
Yeah. And
I did an episode on this called "Truth at the Speed of Smell," because I realized that when my wife, it was Christmas time,
it seems to move too fast. Why does the sense of smell move so fast? Like it can't just be this and this. There's got to be something. If that's true, that's fascinating.
Dude, I did an episode called "Truth at the Speed of Smell," and we my wife did this side hustle with Rover. And so Christmas, we were watching 6 different dogs, and it was like a huge game of Who Farted all holiday weekend. And there was a dog, Otis, that was so just horrified as a pug. It's like a pug looking. It's just a.
I know. I love them. I can't breathe. That's so adorable.
I know. I was in the kitchen, and Ashley was in the living room, and you could hear him fart. He'd go like that. And it was like I smelled it instantly. I was like, "Oh my god!" And then Ashley's like, "Oh my god!" And I was like, "Hey, when did you smell that?" She said, "Right before you said something." And it happened so many times that it's just absolutely unequivocally
impossible
true.
for it to be like. There's no way it could diffuse that
there's
fast.
no way.
No matter
There's no
what,
way.
like how volatile the fume was or whatever.
No, it's charge propagation. It is, and I was like, well, if that's true,
this
then
seems a remarkable performance considering that the sense of smell is regarded to be a relatively slow sense compared to the auditory and visual senses. Odor discrimination tasks and different species show that 200 to 600 milliseconds are required for
but
odor
that's
recognition.
just from smell to brain reaction, though. That's not. But I'm
that's
talking
not the
about
actual
travel.
traversing.
I'm
Okay.
talking about travel through space. The speed of smell is now often. I mean, I think our nasal capacity, our nasals, our sense of smell,
several hundred meters per second.
Yes, 100%.
Okay.
But it's not odor molecules.
If you take a puff of a vape pen or something like that, you
you.
blow it out. It doesn't look like it's going out hundreds of meters per second.
It's charge. I promise
Yeah,
you.
there's no way that any gas could diffuse that fast. There's no
it's
there's
charge. I promise you, it's charge.
That's bizarre. That's crazy.
And if you look, look, all charge neutral substances are odorless, all of them.
So that means if you have the right kind of radio antenna and the right frequency, which is going to be hella high, because we're talking about atom oscillations. But in theory, you could transmit smells as some kind of like electromagnetic wave.
It's charge. It has to be.
Right, but it's not that simple as just charge, because that's charge is just positive or negative. So there's actually some kind of structure to the charge.
Well, that's the thing. It's like we haven't fully solved it, or at least most people would say the Navier-Stokes equations, and that's for fluid.
Or do you think that initially,
if we haven't solved for that, how do we solve for smell?
No, is it like initially just like a really strong positive or negative charge that tweaks us to, oh God, there's like one of those kind of gases, not an inert gas, coming out?
I mean, yeah,
because I just thought it was the molecule receptors. And I'm like,
just think,
how can a smell be that strong? Like when there surely can't be that many molecules. But if it had something to do with, okay,
right. But in the wild, what is going to have that? Only like sulfury, like you don't come across pungent.
No, that's negative. Sulfur is negative, right? I think positive, like good smells, probably positive.
Except for vinegar, which humans have learned, like let's look at ants use it as a weapon, wasps use it as a weapon, formic acid. This is what they inject and squirt at each other during war times, and fire ants bite you and then inject you with formic acid because they're smart and vicious. And vinegar, humans, even though it's really nasty smell and most animals don't like vinegar stuff, right? Humans have said, oh, yeah, that's nasty shit. We're going to make use of that because nobody else likes it. So we can like take advantage of that.
Sure.
You put some vinegar in your kitchen and you're not going to have to worry so much about fruit flies.
We've been using stuff that smells like crap for years.
Right?
Yeah.
Odor receptors.
I mean, like, no, I really got into this.
I just got that. Oh, that was good. Oh, that was good. Oh my god, the citizen. You got me. No, continue. Oh.
Yeah, my model predicts that smell should travel fast because everything is quantum mechanical waveform, which is essentially an electromagnetic field.
Yeah,
so
100%.
There would just be static between your electric field and everybody else's, but then once they came into contact, the diffusion would be accelerated by the magnetism of that field.
Oh, look at that. Smells brought us together again.
Well, you can test the prediction that there should be magnetic induction near the nose, tilting the path of incoming particles.
Yeah, no, and
I just assumed I breathe in.
I'll tell you why I think charge happens. Okay, so 3 quarks make a proton, right? So I think that we live on the 2D holographic surface of a black hole, right? And so in SU1 symmetry, it spins in a circle, right? That's SU1 symmetry. And the only place that matter is real, or the energy is real in that symmetry, is on the y-axis. And so I think that's why I think the holographic surface of the black hole is the y-axis, and the energy oscillating through it becomes matter when it hits the top, and then it hits the bottom. And so, and that's your matter, antimatter, that's your quantumly entangled particle pairs. But if you imagine that you had a proton, which is 3 quarks, and if it's oscillating through this hologram, and it hits down here, and it's going forward in time, or I should say it's spinning this way, and it hits up here, it's going forward in time. It's got 2 up here, it's got 1 down here, so there's gonna be pressure as it punches through the hologram, so that there's gonna be plus here, and there's gonna be a draw here. I think that's the positive and negative. And as this proton comes back around and comes through, now it's going back in time, and it's opposite charge because now there's pressure down here and it's drawing up here, and so that's your antiparticle, right? That's your so as this energy oscillates through, this is where you get your quantumly entangled particle pairs like this. Now, and the electron, right, is going to get sucked to the place where there's less pressure, right? Because it's going to get drawn in. That's what charge is. That's what I think electrical charge is, and it comes from the oscillation of matter through the hologram. Now, if it's 2 units wide, right, then 4 pi, essentially it's a four sort of unit diameter. So the circle is 4 pi. So, and if the hologram is 1 thick, then it's then what you get is essentially, if it's off the hologram, the length that it's off the hologram, if that's dark matter essentially. And if you do the math, then you get 4 pi is the whole orbit. 2 of those is matter is real, and off the hologram, that's the dark matter. So yeah, 4 pi. Yep. So that's why the ratio of dark matter to matter is about 84 to 16%. So, but that's where charge comes from, as I think is differential pressure in the hologram as it punches through. There's more pressure up here, so it draws in this way. That's why this is negative. And
so the claim is would be a mode for inducing oscillation, which would then
for charge. But
the oscillation of matter leads to charge, because as soon as you get something moving or spinning, 100%, you induce 100%. The other. Okay.
And I also did an episode called 1 + 1 = 0, because I think, and this is the reason that stars, when they supernova and they don't leave a black hole, they leave a giant fucking ball of neutrons. It's a neutron star. And the reason is because when you have a proton here and a proton here, and they scissor like lovers, right? It becomes this, whatever this is. It's an octahedron, something like that. Anyway, but now when this piece, see, it's symmetric everywhere you turn it. So now when this punches through the hologram, it doesn't have a differential pressure anywhere. That's why, and it swings back around, same. So that's why 2 protons is a neutron. Now, the difference is, the reason people don't realize that is because in my TOE, mass varies inversely with velocity, right? Because everything that moves at light speed is massless. Everything that almost moves at light speed is almost massless. So your cosmic rays and all that kind of stuff. So now when you think about this spinning, it spins this way indeterminately. And that's why it's just 2, essentially. It's essentially
so you think there's a locked axes?
Yeah. So yeah, definitely. So it's essentially two up quarks is a 2 up quarks is the mass of a neutron, which looks a lot like a proton, which is 2 down quarks and 1 up quark. or 2 up quarks. When you know what I'm talking about, you can look at. But anyway, but that's why they appear to be, and that's why solar fusion is all fucked up and it's just a giant spaghetti mess. But it's really mass varies with velocity, and since this is indeterminately spins, these 4 become massless. These 4 quarks become massless, and you have two down quarks. I don't. Which one's heavier, up quark or down quark? I don't remember. Anyway, whatever.
I think it's down on the. Actually, no, I don't even remember. I
can't remember. One of them's twice the weight of the other one.
Yeah.
So that's why
that just brings. Oh my god, that just brings up. It's like, okay. So very often we assume it's like, all right, we're on the Earth, we're chilling, we're actually cruising through the cosmos. We're doing this. The sun is doing its thing. We're looping around the Milky Way, and the Milky Way is going somewhere. I'm like, wait a second. Would that mean like if we're basically if there's a galaxy and it's moving faster than us? Would that mean the stars might give off different things because they're moving
stars
faster?
Sabine Hassenfelder just posted a paper talking about how stars that are further away from the center of the Milky Way. She said there's a paper that said there's less dark matter in the middle of the Milky Way compared to the outside. That makes perfect sense because the faster something moves, the less it weighs, and the stuff's pinwheeling around the middle of the Sagittarius A star. So the stuff that's closer into the middle is going to have less dark matter than the stuff that's further out, because essentially the faster something moves, if something's going to stay at the same energy, right? If the faster it moves, the more that energy is converted into kinetic energy, but it's still there. Then to stay at the same energy, you would have to transmute some of your mass into dark matter to stay at the same energy. And that's why I think in particle collisions, when all of a sudden, boom, you have a muon, it's really just an embiggened electron, because it used to be spinning around at close to the speed of light in orbit around a proton, but then that proton gets annihilated in a collision. Well, now it's not spinning around anything. And so
you think it's that slowdown that hasn't taken
velocity
that larger.
drops. So it has to embiggen to stay at the same energy. But then when it gets picked up by a positive ion somewhere, it'll spin back up and then it decays back into an electron. And so, but anyway, so when Sabine Hassenfelder this week, she posted something and she said, oh, there's less dark matter in the middle of the galaxy. I was like, yeah, that makes perfect sense, because, I think observable mass varies inversely with velocity. And you can see from this, when I talked about, like, so if we live on a holographic surface of a black hole, and if this thing is spinning around through and it's observable here, now it's dark matter, now it's observable here, now it's dark matter. Well, when it's along this whole trace, right, it's still tugging on the surface of space-time, right? It's still deflecting the surface of space-time. And so that's why dark matter still has gravity, because even though it's hanging off this, even though it's swinging outside the hologram and it's unobservable, it's still tugging. Yep, there's less dark matter at the core of the Milky Way. There you go.
I really need to join
100%.
Fraser's Patreon because I want to use his stuff as sources, and I feel like I should support independent journalism.
Yeah, 100%. That's exactly. Yeah.
Well, I would suggest that dark matter condenses into matter because dark matter is decayed neutrons from the cyclic process. So it'd be protons and electrons soup. Sorry, I'm in the kitchen making food for a sec. And then that slowly turns into
I was going to say, are you actually making soup right now? That'd be very fitting.
I mean, tea.
Okay.
The
caffeine of soup.
Leaf soup. I'm making some leaf soup.
See, I'm not even that exciting. I'm beginning to feel more and more like dark matter is probably pretty boring. My personal opinion is I think there's a lot more neutrinos, and our realm is a lot older than we think it is. And if it was older, there'd be more black holes or more cool matter cooling down.
What's keeping the particles
I think our matter is dark matter. We're made of dark. I mean, dark matter is dark
particles
matter.
apart.
What's that?
What's holding the particles apart?
What part? Which particles?
The ones you claim exist. What's holding them apart?
No, I think they're oscillating. I think they're held by gravity, which is essentially the Higgs string, which
so they don't
I
create
think is
gravity.
The leash. I think it's well, I think gravity is the deflection of space-time when this oscillation. Because essentially, I think the Higgs field is the leash that leashes all the energy and all energy and matter's energy. But in the case of matter, so it's leashing the energy to the surface of space-time, and that's why when it punches through the hologram, that's when it's observable. When it's off the hologram, it's unobservable.
Do you realize that you answered a question that I didn't ask?
No, I'm sorry. Go ahead.
I asked you how you
question.
justify the existence of particles. Specifically, what keeps the particles
It's the intersection
separate?
it's the intersection
So
of
you
the
can't
energy
answer my
with the
question.
hologram.
What keeps the particles separate?
Which particles?
The ones that exist.
Which particles you're talking about?
All the ones that you're claiming exist.
I think it's a question about space.
Oh, it's a
question of whether particles exist, and I'm saying, on what basis are you saying particles exist? And you don't have a basis because you need energy to separate particles. You launched into a non sequitur.
Energy is the U1 oscillation through the surface of the hologram. When our consciousness, I think, our consciousness gets its information from the hologram. So when that U1 oscillation intersects the hologram, that's when those particles become observable. So what keeps what particles, I think there are a bunch of different forces, but the Higgs field, I think, is the leash that leashes the energy to the surface of the black hole. That's why it goes in a circle. And that's why it's that leash that tugs on the surface of space-time. That's why matter deflects space-time. Don't talk to me about that. That's Einstein. He figured that out. But it's that oscillating through the hologram that deflects space-time. And so that's why matter, energy, deflects the surface of the hologram, because it's leashed and it's spinning around in a circle. And it's that tug from that leash that I think deflects space-time. So I think, I think there's a phenomenon that is fairly observed called entropy, where a concentration, essentially it's like osmosis, like a concentration of particles tend to push away from each other.
So
if for no other reason
than evidence for particles.
Say what?
Entropy justifies particles then?
No, I thought we were talking about why they separate.
No.
Why are they separate? Why are there different
I'm trying to
kinds?
answer your question.
Why are there different kinds of particles? Why are there?
I think it's like the
why are they
numbers
separated into different kinds?
It's a useful idea.
Just energy.
Okay, which makes it not real, right? Something being useful turns out makes it not real. So again,
I don't know, man. I mean, it's real if you
you're
can
reasoning
touch it, right?
on the basis of something that's not real. Does that seem like a concern at all?
Just on the basis of observations, you seem to fit.
Yeah.
Right?
So
we've observed it. To be fair, no. Jen is correct when she says we've observed properties from these things that we have identified as and given them the name of particles because we observe these particular properties given these particular circumstances.
Yeah, I mean, I don't know, they model.
It's question begging.
No. You know, well, even at the monastery, we're getting more and more. It's like we should probably address this.
I think it's okay to question beg, but you should know what question you're begging. You should at least know how to back it up. And this justification for separation of anything, it fails. We non-dualists figured that out a long time ago. That's why our system never changes and is always right, because we know that separation is fundamentally impossible.
Well, separation.
It's a part of the system when you are a piece of the whole and everything. It's like, what are you saying? I totally agree. The concept, particles are useful ideas. Like an electron, it's a useful idea, but we should understand at the root of it. It's like we are observing particular properties based upon these whatever you want to define them, a constant of nature for this. That's how we go forth and use these things that we call numbers because we're trying to quantify different things and use them for useful purposes, hopefully.
I mean, I think if what you're trying to say, if you're trying to say, we could view things in terms of fields, like an electron field on the holographic surface.
Like,
and
no,
everything is
like
just a
I'm
field.
exactly saying, no, we can't view things in terms of anything because we have to know why we're using a model before we use it.
See, I don't think that's true.
Well, look at you. You've got a model that's completely incomprehensible based on particles, and you can't justify particles. That's a mess.
I don't think so. It's just like
now, if
saying
you'd have justified the particles at the beginning, you wouldn't have this problem. This is why I never accepted the Western paradigm of thought, because I know its principles of thought are wrong. I don't accept.
But Jen, if for Brad's purposes, he builds something that achieves what he's looking to do, I mean, is that not something?
I mean, if I built something that works, then it works.
He's trying to build a TOE.
No, I'm not. I just have a TOE. I'm not trying to build one. It's once I figured out anti-gravity, that's when the TOE started to make sense. And then so I podcasted about it, and then all the things that I see coming out. The funny thing is that the ignition facility, the National Ignition Center, or where they did inertial confinement fusion, you can't figure out why when they do hydrogen fusion they can't control the residue of that fusion. They can't control it. They think it's high energy ions. Look it up. It's not high energy ions. The reason they can't control them is it's fucking neutrons, just like I said. And so if look up the problems that the National Ignition Center has controlling the fusion residue
on the basis of particles. Neutrons do not enter my reasoning.
Well, okay, but then you're kind of useless when it comes to talking about fusion then, and the residue of inertial confinement fusion.
You don't understand my model, so how would you know?
Well, I'm just saying it because they're talking about particles that they can't control. And so if you don't believe in particles, then how are you contributing? How are you able to contribute to that conversation?
What would say is you observing some form of mass interfering and mucking up.
One of the many reasons you can't control your reactions is because you're trying to force it into a particle ontology that doesn't exist.
Well, so
your predictions are wrong. So of course you can't control the
my prediction was right. My prediction was right. They wouldn't be able to control it. If it was helium, if it was some kind of then they should be able to control it, but it's not helium, it's neutrons. That was my prediction. I predicted from my TOE that hydrogen fusion, you fuse 2 protons from hydrogen, it turns into neutrons. Boom. How about that? Neutrons.
It's a bunch of neutrons. Well, I mean,
if it was hydrogen fusion, it should be helium according to the consensus.
My model can account for this stuff and more, and actually make novel predictions. So
mine did.
What you're doing right now is you're going in circles in your particle ontology, and you just keep repeating your fucking particle numbers. It's like, I'm never going to reason on the basis of particles. I get to be right.
No, that's not true.
No. I don't think there's a disagreement here. He happens to be using a fairly standardized nomenclature a lot of people use. That's all.
And I made a prediction before hydrogen fusion was achieved. My podcast episode came out 2 years ago. 1 + 1 + 1 = 0. That was like 6 or 9 months before they come out and said that they achieved fusion. And then later they said, "Oh, it's tearing up our reactor. We don't know how to control these high energy ions." So when it comes to predictions, I'm making them, honey. So
I think that's why pretty much I have everyone on here, because everyone on here said things that I'm looking at. I'm like, well, it seems like a lot of these different things are panning out in different directions. So I mean, it's like, all right.
So I mean, maybe you got better predictions than me, but I'm making them, and they're turning out to be right. And same with what Sabine Hassenfelder posted about there being less dark matter in the center of the galaxy than fusion.
So that doesn't really change anything about particles not existing.
Well, yeah, I mean, that's cool.
I have to be fair. I'm not sure I would necessarily go that far because, to be fair, it probably does scare a lot of folks off. But I think our conceptualization of what we're
What kind
actually
of hydrogen
we
were
should.
they using? Were they using just regular hydrogen, or are they using deuterium? Do you
Let me
know?
see.
Well, okay,
Continuing the conversation.
I think they may have been using, and I think they may have been using deuterium. The difference between I think deuterium and hydrogen and regular hydrogen.
They're using both.
Yeah, I think they're using both. But deuterium I think is really I think deuterium is like a hydrogen right here. It's like two hydrogens.
Well, deuterium is hydrogen with like an extra with a neutron on it. Why? So because it means two.
But
Yeah,
tritium
that's the
hydrogen with
classical
but I don't think that's what it
description.
is. I think if you have two, like if you have like two protons and you sandwich it like this, now this is not consensus. I agree. This is not consensus. But this is a neutron, right? Like this. A deuterium is when you get it weird.
No, don't say that.
No,
I need
Kali
electron
loves
capture.
those. No, as soon as you
I
start
need
doing that, I'm like,
electron
Kali has her
capture
vertices and
desperately.
stuff.
A deuterium is instead of two gluons scissoring like that. I think a deuterium is when you get one. It's like poking through. So it's this kind of gnarly, weird shape. It's kind of like an almost neutron, but it's not symmetric. Essentially,
Or it's like if they
one.
were joined at the vertex and they had their
Yeah.
spikes sticking out instead of like scissoring, like completely inversely constructed.
Yeah, you get one jammed right through the middle of like the triangle. That's deuterium. And there's
you missed this whole thing earlier about these. What I did with, and this is totally just a weird convenient model for quarks, right? Like this would be a up quark.
Okay, but wait a minute. But why do you have like four vertices like that?
I consider them the fractional charges. If we consider the fractional charges axes of charge.
Okay.
So there's two fractional charges. There's a third fractional charge. Now we're going to make a proton. And there's this. So I'm going to take this positive and this negative, and I'm going to squish them together and make them into a photon, which is those two charges put together, basically. And I'm going to make them chase each other's tail in the middle, which creates like a mass particle because it's all inertia, because it's all in orbit, right?
Sure.
So it's just like a sphere of inertia because it's trapped in orbit around itself.
Just light speed energy, okay.
Right? And then there's also left over 3 additional charges, right? Oh, that's it. Protons 2 ups, 1 down. 2 up. 4 positive, 1. We take this one, nullify it. We have 3 left over, which makes a perfect Cartesian axis of charges, which makes perfect sense for like charge, electric charge, magnetic charge being 90 degrees opposed to each other constantly.
Okay.
As being an innate structural thing from quark fractional charge construction.
Okay. I think I'm with you.
It just tweaked me as you were doing that diagram about like ways of approaching the geometries of the way probably it seems like space seems to like flow in these weird vortices or whatever that construct, and then these vortex constructions that somehow self-organize in space is particles, and then inflows and outflows are the chargy parts, and rotational parts we consider mass because they just sort of sit there and they don't really do anything, like they don't have an inflow or an outflow. They're just purely rotational, and therefore they have like the inertia of rotation without an inflow or an outflow, so there's no charge part. Like that would be
well,
a neutron.
but okay,
It's
so the
just be
difference though
spinning.
is that you think the universe is three-dimensional space, and I think right, you're describing a three-dimensional
almost
space,
always
seems like.
in terms of the space that we interact with.
Mhm.
I think that it suffices to have three-dimensional, not three dimensions, because as soon as you have a fluid, flows in a fluid are very badly described by three dimensions. Like it really is. It's sort of like when you start to have multiple vortices in the same volume, describing it in only three dimensions doesn't make sense, because there's a fraction, there's a like a fractal dimension to the texture of these convolutions in space. So that's why it's like I generally try to think, I think of space as being an infinitely continuous fluid that self-excites. And because it self-excites, that means that it spontaneously moves itself towards maximal density. It wants to be all in the same place at the same time. And
isn't entropy the opposite of that?
But gravity is negentropic, therefore, right? Everything gathers. The energy is concentrated always in the universe.
True. Yeah. Well,
so instead,
okay.
I think it's the way of thinking about it is more like degrees of freedom. When you're a hydrogen atom, or let's say in my model, you're a neutron, you burst open in free space in the middle of a void where there's nothing because it really needed something there, because space abhors a vacuum. So you burst open. So now you're a proton and an electron floating around in space. Each of you has 360 degrees of complete freedom initially. Then the electron ends up getting bound around the proton and becomes monatomic hydrogen, which is not the typical hydrogen. Most hydrogen we know is H2, or like two H's combined. So first monatomic hydrogen, which the electron loses a degree of freedom because now it's caught in orbit. It's stuck on a two-dimensional surface of sorts.
But wait a minute, but you have to, and I know this is me, but like you need beta decay, right? Before you get, right? I mean, like that, I think that protons, and by the way, on the surface of every neutron star is an atmosphere of hydrogen, because when they split,
the neutrons are decaying all the time at the surface.
I know, and they're letting hydrogen go because two hydrogens makes a neutron. So if the whole neutron star is essentially, once you get out of the pressure of, once you're on the surface of the neutron star, this little guy on the surface, right? He's got all these positive. These guys are pushing him off, and that's beta decay. And when he comes off, he's a hydrogen, and that's why there's a hydrogen atmosphere around a neutron star.
We will argue over this mechanism exactly, but
okay, but well, I mean, I just think it. Anyway, bottom line is you need lots of pressure from the core of the star to push them together, and then when that pressure's gone and they're sitting on the surface of the neutron star, it's fighting gravity, of course, but they come off. But in order for you to get a loose hydrogen, are you saying that neutrons accept an electron?
Neutrons decay. A free neutron decays into, and we're just going to use like terminology, a proton and an electron. This is what a neutron decays into.
I'm not sure I agree with that, but okay. No, I don't think they're. I don't quite think they have it, but okay, we'll just go with that.
And a neutrino, but I'm just going to let the neutrinos slip off to the side because we don't need that till later.
There's a proper accounting.
So you have a proton and an electron. Trust me. The proton has the mass and the positive charge. The electron's the compensatory negative charge. So when it first decays, you've got these things that are floating around that are not associated with each other. Both of them have 360 degrees of freedom. Then it loses a degree of freedom, the electron, when it binds itself to the proton. The hydrogen now still has 360 degrees of freedom. As soon as the hydrogen bonds with another hydrogen, making H2, which is the hydrogen that we see almost every place, it just lost a degree of freedom because now it's got an attachment along an axis with that other hydrogen. And the entire journey of all matter is losing degrees of freedom because you get into larger and larger molecules where you're like more and more confined and more limited, and you have less and less space and more energy crammed into that space, more and more movement. But it's not, that's the thing. It's like entropy is a complicated thing because temperature, you cannot have a single object can't have a temperature. Like a baseball can have a temperature because it's a bunch of things, but a single atom in space can't have a temperature because temperature is purely a measure of the interaction of particles with each other. Mm-hmm. How often are they bumping into each other? If something's not bumping into anything, then it's absolute zero, right? And then that's the principle. So it's a weird thing where as you get closer and closer and more dense, as you lose degrees of freedom, it's maybe not the losing degrees, you're losing space of your degrees of freedom. You had infinite space when you're an electron and your charge completely roams limitless. Now you're confined to a hydrogen orbit. Now you've got two hydrogens confined to only a slightly larger orbit than that original hydrogen had. And that whole progression is confining more and more energy into less and less space. You have the same degrees of freedom, but they're in less space. So that's the compensation is essentially temperature, which is a measure of energy in a weird sort of thermodynamic, like at the root, movement is a thermodynamic attribute because it's going to bump into something unless it doesn't, and then it has no temperature at all because it never bumped into anything, right?
Yeah. No, I definitely, yeah. I mean, I get what you're saying about temperature because that's when we talk about my toy. That's how I figured out, or that's how I sorted out what we needed to do to achieve anti-gravity. So it's all about heating your food in a microwave, right? Because when you heat your food in a microwave,
you want to give us the full promo, the full.
Sure. Okay, but we were talking about the reason heat and temperature comes from interaction is a lot like how you heat your food in a microwave. You put your food in the microwave, you turn it on, and it bombards it with microwaves.
Oscillates.
And microwaves are like, low energy,
like H2O or something.
Yeah, no, it's like, it's like lower energy electrons, right? And they bounce off your food. They bounce off your food. And it causes your food to jiggle, the little atoms in your food to jiggle. And if you heat it up too much, they'll jiggle and they'll break away and they'll break those bonds and release energy, and that's flames, right? So you're burning your food. But when you heat your food in a microwave, microwaves hit and they bounce off the molecules of your food, and your food jiggles. And that's how you heat up your food. That's how you put energy into your food. And so that was instrumental in anti-gravity for reasons that we can talk about in a second.
But, well, there's that one anti-gravity device that the premise, though I thought the angle was wrong on it, the premise was that basically by you output a signal, and because your horn expands on the one end, which makes the wave like expand out, which lessens the energy density, which thus creates an energy imbalance between the two ends of the space, because you have a really, really high energy density at one end where the horn itself is, right? where the emitter is. And then the back end where the horn is, the energy is expanded considerably. And if you can create a phase blockage there, basically, so you create a permanent wave trough on one end by creating a standing wave with a trough at one end and the node at the other, which would make you impel towards the node end because that end has always got more energy than the trough end.
Yeah. That might be like a form of propulsion. The trouble, though, is that
I thought that was the one that they shot up into space recently. That was the premise of that. Like,
I don't know. The one thing that I think that is critical in order for, UFOs to fly and all that stuff to work is that the mass has to go away. Somehow we have to reduce observable mass because, and maybe this is a good place to start. So I did not believe in UFOs or anything until 2021 when the Navy said, yep, that's a UFO. It's floating. It's real. And that was enough for me. Like, Navy said they're real. I believe they're real. Period. Like, I trust the Navy, right? So I'm a retired Army. So like, I don't think these Navy pilots would be saying these UFOs like weren't real if they weren't real. So I decided that, okay, I'm not going to, no more discussion about whether or not they're real or not. That's already decided. So the only question for me then is, okay, how do they fly then? How do they actually do it? Because I'm seeing them do it. I believe the Navy. So how do they do it? I got to figure it out. And one thing I noticed was that, like, they talk about this instantaneous velocity. Now, force equals mass times acceleration. And so the force that you would feel from accelerating instantly is exactly the same as the force that you would feel if you're going 1,000,000 miles an hour and then stopped instantly, like crashed into a wall or something. So force equals mass times acceleration. So the bottom line is that any ship, whether it was a drone or was a ship with people in it, it doesn't matter. It would crush itself on acceleration with this instantaneous velocity business, no matter what. I mean, so it wouldn't be a drone. Like, a ship would just crush itself like a pop can if it accelerated like that. I mean, what it feels like to accelerate in your car when you're just going like 0 to 60 in a few seconds. You feel like totally crushed into the back of your.
I know, I've been thinking about that, but it seems to me like if you put 3 properly gimbaled rings interlaced with each other, so that whenever you try and move this object in any direction, instead what happens, like if there were gyroscopes, instead what happens is that one of the gyroscopes starts rotating around one of its axis instead. Like, it would always, everything that would seem like a ridiculous, impossible thing would just end up spinning another part in compensation, because this is the conservation of angular momentum. Any forward velocity, you can pivot around it, and you could stay still and everything else would pivot around you, sort of thing. Or you would pivot to compensate for that. You would be rotating crazy fast as a way of absorbing that kinetic energy that you had to compensate for with that change. I mean, there's got to be some kind of weird math thing, but I've been trying to figure out, how do you get away with this shit?
Well, that's not how I did it. That's not how I figured it, but go for it. You know what I mean? But I just figure if you're going if you're like taking off at instantaneous velocity, the mass has to, in my view, the mass has to go essentially to zero. You've got to be massless in order to survive that acceleration, or in order for the craft to survive.
That's why I moved to Utah.
Yeah. So.
Dimensional mass. I'm sorry. No, I'm sorry. I'm masshole born and raised. So sorry. I hear when you say you have to go massless, I'm like, Like I kind of did. I'm
No,
there
you
right
have to
now.
create a mass hole. You need a mass hole. And so,
Okay.
so
There's
anyway,
one.
so I was
let
like,
me
well,
hit Schrodinger status. Continue.
yeah, no. So I was like, well, what gives matter mass then? What gives matter mass? And it turns out I was watching PBS Space Time and everything, and found out the Higgs field is what gives matter its mass. The interaction with the Higgs field is what I guess the consensus.
It appears, to my knowledge, I'm sorry, I think it's a coupling, and it accounts for probably about 2%, to about 2% of mass, and then it's like.
No, it's the weight of the Higgs boson is not the weight of matter. So it's kind of like Higgs boson. Think of it like a rubber band, right? Like it maybe it's only 2% of the weight, right? But it's the strength that it has, like the force that it can generate is sort of the Higgs field.
Well, you're talking about like the elasticity or inelasticity, like the tensile strength of what we conceptualize as space time. It's dude, no, that's wicked strong. See, this is where I kind of get confused because I feel like it was a hack to give the electron its mass. I felt like it's a spin one couples, so it gets just amount of mass, and the rest is rest energy or c squared, whatever.
But methodology. Let's forget interpretations. Let's just talk about what did you do. And what happened?
Okay, yeah. So here's what I did. So I found out from PBS Spacetime that the Higgs field is what gives matter its mass. And it turns out then, so I was like, well, okay, so I need to cancel the Higgs field. I need to get rid of the Higgs field so that it won't give the ship mass. So I was like, well, how do I get a hold of the Higgs field? And it turns out that the left-handed electron carries weak hypercharge, and weak hypercharge is what it gets from the Higgs field. The Higgs field is an infinite source and sink of weak hypercharge. And so I said, well,
but
okay,
not the right-handed electron.
So I think, well, this is later on, my theory of everything came from this, but so I think the electron goes like this. When it's going forward in time, whatever, it's an electron, and when it goes backwards in time or whatever, that's when it's the left-handed electron. But yeah, so the left-handed electron, they said, trades the weak hypercharge back and forth with the Higgs field. That's not me. That's Dr. Matt O'Dowd on PBS Spacetime. That's where I got that. And so I'm like, well, okay. So if the Higgs field is what gives matter mass, and the left-handed electron is stuck to the Higgs field, then how do I get a hold of left-handed electrons, right? That's the next step. How do I get a hold of left-handed electrons? And I found this 2009 research from a Dr. Lawrence Eves at University of Nottingham, and he was playing around with what they called graphene. And graphene is like a sheet of carbon, like one atom thick. And the cool thing about graphene is it arranges itself it's all hexagonal lattice.
Yeah, and it forms spontaneous, electron vortices in it and stuff like that when you have sheets of it.
Yeah.
Right.
Okay, so what he said this is what he said, and I'm just going by what he said. But he said when you pass a magnetic field perpendicular through the graphene, that hexagonal lattice splits out left and right-handed electrons, and it holds those left-handed electrons in what he called cyclotron orbits inside the magnetic field. They just fucking float there. That's what they do. That's what he said. So now I'm like, okay, so if I want to get rid of mass, then I need to cancel the Higgs field, which means I need to use left-handed electrons, and I need to I can catch them in a magnetic field if I pass a magnetic field through a hexagonal lattice. And so what I did was I created a Faraday disc. And a Faraday disc was invented by Michael Faraday like 200 years ago. And what it is, it's a copper disc. And when you spin it and you put like a magnet on the side of it, magnet
homopolar generator. It's like the original motor.
I'm trying to tell everybody that
sorry.
It's okay. The magnet pushes the electrons from the outside of the disc into the middle, and that makes it minus in the middle of the disc. There you go. So it's a minus in the middle of the disc, and it's plus on the end of the disc. And if you connect the middle of the disc, see right there, see how that See how that little wire connects the middle of the disk where the electrons are getting pushed to the outside of the disk where there's less, where it's plus. It's like connecting the plus and minus sides of a battery.
Oh yeah,
And,
actually,
and
story.
so,
I read the original write-up by Michael Faraday about this. It blew up in his lab.
Wow. How about that?
He got it to feed back, and it just sped up and sped up. He writes this in his journal, and it flew off the table.
Get the fuck out of here. Well, I mean, yeah, I believe it. Well, I mean, that is,
Sorry, so
if I get
finish
this
your
right,
story, because this is
if I get it right.
Yeah.
It's crazy. So, but the beautiful thing about a Faraday disc is that the disc shape. Now, anytime you have a flowing current, right? If you connect the middle of the disc to the edge of the disc, current will flow, like connecting the plus and minus side of the battery. And anytime you have a flowing electric current, you have an electromagnetic field. It just happens in physics, period, you get one. But the beautiful thing about a Faraday disc is that the electromagnetic field blows through the surface of the disc, curves back around, and comes back and blows through the backside of the disc. And so now you're starting to see that, hey, like maybe there's a reason that these saucers are saucer shaped, right? So the magnetic field blows through the surface of the disc, comes back around, and comes through the back. Now, so if you take, I was using graphene and nickel, because nickel is a hexagonal lattice, graphene is a hexagonal lattice. And so I did all these stacks and stacks and stacks of nickel and graphene, right? And the idea was that when I take my Faraday disc and spin it up, and the magnetic field blows through the surface of those, I want the left-handed electrons to tease out and float, like they're supposed to. Then here's the thing. The vacuum expectation value of the Higgs field is 246 giga-electron volts, right? That's the consensus physicist understanding. Like, I'm not making that up. 246 giga-electron volts is the energy density of the Higgs field in a vacuum. And so the only thing that deviates from the scientific consensus is that I think the Higgs field is not positive 246 giga-electron volts. I think it's negative 246 giga-electron volts for a lot of reasons. Bottom line is that I think gravity is the Higgs field. Gravity is negative energy density. And so I said, well, if I'm right that the Higgs field is 246 giga-electron volts, is negative 246 giga-electron volts, not positive 246, then if I can essentially create that magnetic field, and then just like the food in your microwave, right? If I can jiggle those left-handed electrons that are in my magnetic field, if I can jiggle 246 giga-electron volts into those electrons, and if those electrons are stuck to the Higgs field, then I'm jiggling 246 giga-electron volts into the negative 246 giga-electron volt Higgs field, and I drop the Higgs field to the ground state, and now everything that is in that electric field must be massless. If I'm right that the Higgs field is negative 246 giga-electron volts.
So, because the Higgs, it's normally about like about a 125 or maybe give or take. So you're taking about twice that to account for like the amplitude of it, or the full range? Or?
246 giga-electron volts is.
Or so that's the coupling for the electron.
My understanding is that that's the vacuum expectation value of the Higgs field in the vacuum. Period. I'm not adding anything or subtracting anything from that.
I remember saying that. Yeah. I'm just according to Wolfram Alpha, that's twice the Higgs boson particle. Okay.
Yeah, I don't know. I mean, I'm just going by. I'm just going by. Dr. Matt O'Dowd from PVS Spacetime said that the vacuum expectation value of the Higgs field is 246.
Why the nickel? Because the nickel has a hexagonal structure as well.
The hexagonal structure as well, and if, by the way, if you look at like the fragment of the UFO fragment that Tom DeLonge found, that bought, it's magnesium, bismuth, and zinc. Guess what the molecular structure of magnesium, bismuth, and zinc all are? They're hexagonal. They're hexagonal.
I mean, hexagons are good at going together. That's how we get the
now,
dodecahedron.
And his is a nano-layered bismuth, magnesium, zinc.
Isn't bismuth cubic?
Yeah, maybe. I don't know. That's just what he said his was made of. So
I think the claim was it was very interesting to find this particular makeup of these things, and that's totally. I heard that from Professor Keating. I think
what I would give to get a like electron, like a good scanning electron micrograph, or like a tunneling electron micrograph of some of those materials, like a decent slice of those materials.
Well,
to see what the structure is,
but essentially by basic engineering, just basic problem solving, what gives matter mass? The Higgs field. How do I get a hold of the Higgs field? It's a left-handed electron. Okay, how do I get left-handed electrons? Oh, Dr. Lawrence Steve says you pass a magnetic field through graphene, it teases them out and they sit in your magnetic field. And so, so I built my Faraday disc. I call it an amp, the anti-gravity amp, this nickel and graphene sandwich. Mine's really ghetto, I can only build with what I can get on Amazon, right? So essentially I built this Faraday disc that spins. I put this, this ghetto sandwich on top of it, and I turn it on, and I put the whole rig on a scale, and then I turn it on. If it works, it should get lighter, right? And it did. Got about a half pound lighter. It got a half pound. I sent you the videos of it, and I built a couple of them. I built 4 of them so far, and one of them I built. The very first one I built. I got like 2.5 pound swing, where it was like sitting at like 25 pounds, and then it swings up, and then it comes back down. And I think the reason that it did that is because it's the I didn't finish. So in order to essentially jiggle the left-handed electron to put energy, the same way the microwave heats up your food and jiggles your food. So I take an oscilloscope, and then I attach the oscilloscope to the Faraday disc. And an oscilloscope can create a signal like a pulse. And so I have this thing spinning. I pack my field with left-handed electrons, and then I take my oscilloscope and I put that signal through a car stereo amp to jack up the wattage, and then I push it through the disc, the contact on the end, the contact. And then I turn it up to, a few. I mean, I was playing around with megahertz and kilohertz and all that kind of stuff. But essentially what I do is I jiggle those electrons that are sitting in that field by turning on that oscilloscope, and then, thumping by
like adjusting the frequency and everything.
Yeah, by messing with the frequency. And I think if those electrons, those left-handed electrons, if there's on the Higgs field, if they're sitting there, to jiggle them, it's like pushing a kid on a swing, right? You got to push, they got to come back, and you push. And so it's that harmonics. It's getting that signal frequency right that will get them to jiggle. Because if you're pushing the kid when he goes out and then comes back and you push him again, if you get that harmonics right, if you get those harmonics, you can reach what you call resonance.
You maximize as a child. I love to swing, dude. It's rhythmic.
That's what causes the Hutchison effect stuff with all that weird melty metal. It's because you see, it's like it's almost always in the middle of a bar of metal, because obviously what's happening is all the radio, because he just has these insane transmitters and stuff in his apartment. Imagine filling your apartment with microwave guns and just standing there. He's crazy. But anyways,
that's a good way to get cancer or something.
Yeah.
But I was gonna say that sounds like the scene in The Expanse when all of a sudden they're exposed to all this radiation and stuff like that.
When you hit the right frequency, when you hit the resonant frequency, it's like when you're tuning your oscillators and whatever. I mean, sparsely spark gap oscillators.
There were bridge accidents because of that, I think.
Yeah, the Tacoma Narrows came down.
You gotta tune it so you can maximize. Yeah. It's like when you're building antennas, when you're doing ham radio, literally a half inch to your antenna could add 20% to your power output. Because if it's not exactly the quarter wave or half wave, then it's just not going to work. Like it's just
Yep.
you're wasting so much pressure because you're not putting it at the right time.
Yep. Yeah. It's a butcher scale. It's 100-pound spring scale. I didn't want to mess with I didn't want the the fields or whatever to mess up the electronics or whatever. So I just went old school, and it's a butcher
Limited
scale.
resources. Yeah.
Yeah. Well, I didn't want to use a digital scale because
because you could mess up. Yeah,
you're using
electrical
piezometric
sparks
stuff.
will screw up that shit so bad.
Yeah.
See, my only concern there, Brad, is I'm like, seeing it do something, that's absolutely freaking amazing. My thing is, especially since if this is the first time really building stuff like this, can you account for if there's rotation? Is there are we accounting for the rotation? Because I saw some plates spinning really quick, and they were so smooth. When they came down, they were just the air pressure was separating them. So can we account for how much of that is happening versus the actual potential?
Definitely.
Okay.
I mean, I think if the thing that makes me think that it works, and I don't have a nano layered alloy like Tom DeLonge has from his, and the UFOs are carrying, right? So, but Mark Sokol is a friend of mine who owns Falcon Space Labs, said I can come up there anytime and use his chemical vapor deposition machine, and he just wants to watch it go. And so, yeah, so I don't even need DARPA funding for it anymore. I definitely want DARPA funding, and I want this to be mainstreamed. I want the military industrial complex building free energy, anti-gravity turbines, and not bombs. You know what I mean? We need to. I think everybody needs to know how this works. And so anyway, but I create this amp. I turn the oscilloscope on, start jiggling those left-handed electrons, and it looks like it gets lighter. So my next, I've built 4 of these so far. So my next one I'm gonna build with Mark's CVD machine. I'm gonna make the amp.
So you've had consistent replication of the effect.
Yeah.
Okay. No,
Yeah,
dude, that's cool, man. Dude, that's awesome.
Yeah, I mean, I've sent you the video.
Using a spark gap as your actual method, to create the oscillation.
Oh, a what? Yes, you're talking about
okay.
Mechanical frequency modulation.
Yeah, because you have your disc, the spinning disc, right?
The first one I did was mechanically. I modulated the frequency with the mechanic. So there's the third and the fourth prototypes I did, I used the oscilloscope. But the way I created the pulse with the first and second prototypes was so I have the magnets evenly spaced all around the disc, right? And so, but instead of having a plate for a disc, right, I had it wasn't a disc, it was a modified Faraday disc, but there was spokes. So the disc in the middle, the middle was a disc part, but then in a band of the Faraday disc around here, it was spokes. And so when the spokes would go under the magnets, it would give a pulse. Poof, poof, poof. So then the faster you go, the faster the pulse would go. Does that make sense?
Yeah.
No.
And wait, did you look at more Faraday's things? Because as he was investigating it, he ended up taking the disc and cutting the disc in spirals into a bunch of spiraling arms, as a way of slowing down so that the current couldn't just go straight from the periphery to the center, but it had a turbine. But it had to follow a longer route intentionally, so that it would have to interact with the magnet more.
But he only had one magnet, right?
Yeah. But I'm just saying, as a thought.
So I have. See, the trouble with his, right, is if you only have one magnet, then your field is fucking all cattywampus and weird. So I wanted to keep the field nice and laminar. So I have a bunch
like
of magnets.
all north at the bottom and all south at the top, or oppositionally positioned?
No, they're like north. It's like it's like they have to be what you call.
I mean, to be fair, we've been going almost 3 hours now. I mean, if you want it, I know it's getting a little late.
No.
We could do an entire episode on this.
Made it. No, I just made it so I think I made it so that they were repulsive, like like north down like that, because I wanted it to be like I wanted it to like push stuff. You know what I mean? I didn't want it to, you know what I mean?
Yeah,
and I think when he does it, I'm not sure.
You're going for the outward force.
Yeah. Anyway, I don't know. That's a good thing to look at. See, like if one does better than the other. You know what I mean? That's a great idea. That's a great idea for
because there's also a patent I'll look for that's a solid state, not a free energy device, but a weird kind of transformer that uses a similar like oppositional magnets, but then one of the coils runs this way, and then other coils run this way, which is not.
Now, see, here's the thing. If you go like, if you do like this, if you have one disc going like this, and then you have another disc going like this, well, now you're going to have an envelope. You're going to have an anti-gravity envelope. Okay, because just bear with me. If I'm right that this is how it works, and you create this field that goes like this, that's like, now anything in that field is massless, right? Well, if you do another one going this way, and then that field goes, like that, well, now you have this envelope of anti-gravity. And if you're using a hoop, everybody in the middle, you can work the controls, and that's where the pilots go. But then there's this anti-gravity envelope around it where the universe can't tell you, can't communicate gravity to you. So you're massless. I mean, even though you have mass, to the rest of the universe, you're totally massless. And so now, what's that?
I gotta ask the question.
Sure, go ahead.
Do you think that's an effect of decoupling from gravity, or an effect of electromagnetism in some way?
Well, it seems to me that if the left-handed electron is stuck to the Higgs field, and if the Higgs field is 246 gigaelectron volts, and if I shake 246 gigaelectron volts into it, then that's a field. That field is at the ground state.
If we can generate that bubble,
no inertia,
we will have
no
decoupled, and we should effectively
There's no gravity can't get to me if the field works like that, right? And as far as that's the only thing I can think of. And I know people talk about plasmas and whatever, and I don't know, or gyros like you're talking about. But the only thing that I think can save you and save your craft is this actual mass reduction. Like, you have to take your mass to zero. And so,
literally by achieving a particular frequency, if some may say music, we may be able to have a great leap forward.
Maybe. But get this. So now you have this thing spinning, right? And now the Faraday disk, as it spins, generates electricity, right? It shoves the electrons to the middle. It's spinning. It creates a voltage. And so, but now
that's what I mean.
If we get this field geometry right, now the faster it spins, the stronger the field gets. The more the mass gets reduced. The less friction you have, the faster it spins. The more field gets. And so
that's what you have with Michael Faraday. Once he connected the axle to the periphery, he started to get this feedback mechanism.
I think that's probably what it was. Is that essentially, if you get that thing to completely go massless, now it takes very little energy to make it continue to spin. So, so essentially, what you're doing, it's not. Excuse me, it's not perpetual motion because what I think is happening is when the mass reduces, right? Just the same way that I think observable mass drops with velocity, inversely with velocity, I think if you reduce the mass through this mechanism, the conservation of mass energy will generate electricity, will generate energy to compensate for that mass that just transmuted into a dark matter state. So I think, so it's not perpetual motion, but I do think you're creating a state where you're essentially temporarily trading mass, kilograms, for electropotential, for voltage. And so so it would literally be totally green, like renewable energy. Like if it spins faster and gets lighter and spins faster and gets lighter, and then you can essentially divert its own energy.
It's a dimensional currency exchange, if you would. You're trading off the kilogram
exactly
property for basically this form of whatever we are achieving doing this thing, which I mean, that would be fantastic and everything. I mean, I think this is why I think a lot of finance folks and physicists do a lot of the same things, because they're looking for the transformations there.
Yeah, but if it works, then you're talking about free, renewable.
If it works, people make money. No, people make lots of money.
Yeah. I mean, and you're talking about.
I mean, this would be fantastic. Yeah.
Energy everywhere.
Cool.
You know, I mean.
But my big thing, sorry to cut you off. I'm like, we're coming up on 3 hours, and I do have to go to sleep at some point. I'm not going to stop you two from talking if we end this. But how about at least for the official broadcast? For at least the official broadcast, how about let's do this? Kali, why don't you tell the folks what you got going on coming up? Some more stuff on neutron decay cosmology and that collider thing for frequencies, which is fascinating.
Oh yeah, I just been goofing on that. The oscilloscope and the super collider and stuff like that.
I think that would be up Brad's alley personally, but go on.
What?
Brad. I think it would be up his alley or something like that. I know you had some videos.
Yeah. I don't know. I just go with my muse. You know, whatever it says, I do.
Cool. All right, we got Kali. Kali's link is in the description below, and we have the Brad Voorhees Sonic Gravity podcast.
Hey, yeah, man. Hey, thanks for listening. This is just what I'm doing kind of in my spare time, doing some anti-gravity. I just ordered most of the parts, I think, for the Mark V, which is my fifth prototype. I'm going to be dropping an episode, I think, tonight or tomorrow, called Alien Logic Part 2. And it's just kind of my take on why we can be sure that that aliens excuse me are here, and how we can know from the evidence around us. And I got a couple clips of Dr. Keating talking about why he doesn't think that, and so I'm gonna sort of take apart that.
We're gonna have the rebuttal. I feel like your rebuttal might be a little bit more pleasant and well received than other folks, but I mean, I don't know. I don't know. I just
much evidence. There is so much evidence. If anybody actually bothers to look at all the documents and all the interviews and all the footage by all the people from all the places all over the world, just be quiet, okay? Just settle down, you people, because it's just irrefutable, especially with historical accounts from like 17-something, where they come into a town, they have a fight, and then everybody gets radiation poisoning. I mean, come on. Yeah, that just happened. Oh, they mistook a flock of geese for a bunch of UFOs, like they had never seen geese ever before in their lives. Come on.
Well, I just think
geese can be quite scary, especially the Canadians.
I think even apart from that, I think in a sufficiently Earth-like environment, right? You know, water goes downhill. What goes up must come down. The stationary action principle suggests that in a sufficiently Earth-like environment, humans happen, right? Because we're here. You know, there's nothing special. It's, you know, there's something called convergent evolution. There's like 6 different completely unrelated species all evolved into crabs. You know.
Yeah, I was gonna say everything always go with the crabs. I thought crabs are very effective.
Yeah. I know, man. And so in a sufficiently Earth-like environment, I think that it's hard to argue with the observation that in a sufficiently Earth-like environment, humans happen, period, end of story. And so a 14, 15 billion year old universe, right? When, yeah, exactly, Rick. Dinosaurs happened. That's another thing. And so in a 14 billion year old universe, in a 4 billion year old planet, we're here, right? There's no way that we're the first humans. We can't be the first humans because there's billions and billions of other, planets out there that are sufficiently Earth-like to have humans. And so what does that mean? That means that we are an exoplanet colony of an interstellar human species. We have to be. And if you start looking at the fossil record, if you start looking at the sort of impossibility that there's only two species with RH plus and minus blood, it's us and chimps, and there's no evolutionary trace in between. And just for a whole bunch of other reasons, take an 8 billion population and wind it back mathematically using any growth rate that you want. You'll never get further back than 12,000 years. That's a fact. And we're not even really a $8 billion, or I'm sorry, we're not even an 8 billion population. We're closer to 1 billion populations. So anyway, the bottom line is that.
Oh no! I mean that's a spicy conjecture right there, and everything. I mean, I have no idea what the actual answer is. I mean, I don't know. It also sounds like wait a second. I'm like, Brad, are you saying that like the plot of like Prometheus and stuff like that, like they were trying to signal to us in a way? The Alien prequel thingy that they came out with, where it's like they're looking like some of these precursors. They're looking at DNA. It's like it's freaking human DNA. Okay, yeah. It's a little bit different, but it's like, oh my god, this freaking like 8 foot tall kind of like blue dude is like what? It's like I heard that. I'm like, I'm not sure. Do I want to know the answer? I'm like, I'm gonna play with these things called particles. And on that, everybody.
Rick said something that was really sharp, though. He said dinosaurs, and he's right, because if you look at the fossil record, it's laminar up until about 65 million years ago. It's all lizards and dinosaurs, and when you think about it, so if the truth is that any sufficiently Earth-like environment yields dinosaurs. And I did an episode like 2 years ago, maybe, called The Real Prime Directive. And that's when I figured out that, there's a velociraptor called Troodon that has an opposable thumb, language, big brain. And definitely in any sufficiently Earth-like environment that isn't hit by a meteor that only wipes out the dinosaurs, by the way, the Troodon must, if all it takes is time to go interstellar, then the Troodon goes interstellar. Like the successor in evolution to that dinosaur goes interstellar. And so that means that when we go interstellar, we're probably going to find that, in different worlds and different places, different species probably go interstellar. Maybe even some insects. Maybe
so what you're saying is lizards. If and when we have that point of
the prime directive
contact between species, we should not challenge them to a thumb war.
No, but the prime directive might be real. That there might be an interstellar treaty that says we're not going to put our thumb on the scale until a civilization is sufficiently developed. It could be a treaty, and so then it makes you wonder: was the meteor that hit Earth that wiped out the dinosaurs, was that a violation of the treaty, or was it the reason for it? And so now there starts to be existential reasons to shut up people who are talking about aliens, to shut up people who are talking about who are poking their nose in places that they don't want to be or shouldn't be.
God,
I mean,
wait a second. Wait, oh my god, now we Wait. The crazy thing is, I'm entertaining a potential path. I'm like, all right, so if you're a Saurian thing and you're around for millions and millions of years, it's like, would you have developed social media and started to be dicks interstellarly?
Well, I mean, that's just it, man. Like,
we're gonna have to find out next week, everybody, on that. Yeah. We'll catch you all